I'm so glad you found your way here because tonight we're leaving Earth behind and drifting into the deepest mysteries of the cosmos. Wherever you are in the world, let this be your moment to slow down, to let the noise of the day soften and fade, and to allow your thoughts to settle like cosmic dust in the quiet void of space. Tonight, we're exploring 100 mysteries of the universe, questions that have puzzled scientists for generations, phenomena that challenge everything we think we know about reality itself. From invisible matter holding galaxies together to signals from across the cosmos that arrive without explanation. From voids so vast they seem impossible to objects so strange they defy the laws of physics. The universe is not just vast, it's mysterious, beautiful, and far stranger than most of us ever imagine. Some of what you hear tonight may change how you see the night sky. Other discoveries might simply drift by like starlight through darkness, gentle, curious, and quietly unforgettable. If this kind of peaceful cosmic wonder brings you calm or sparks your curiosity, consider liking and subscribing. It helps others find their way here too, one sleepy soul at a time, drifting through the infinite. But for now, let yourself get comfortable, take a deep breath, and let's begin this slow and soothing journey through the greatest mysteries the universe has to offer. Something massive is pulling our galaxy through space. Right now, as you rest, the Milky Way galaxy is being pulled through space at over 2 million kilometers per hour toward something we cannot see. This invisible destination lies roughly 250 million light-years away in the direction of the constellations Hydra and Centaurus. Scientists call it the Great Attractor, and despite decades of observation, we still don't fully understand what it is. Our entire local group of galaxies, including Andromeda and dozens of smaller galaxies, is caught in this cosmic current flowing toward this mysterious gravitational anomaly. The Great Attractor itself appears to be part of an even larger structure called the Laniakea supercluster, a collection of 100,000 galaxies all connected by invisible threads of dark matter spanning 500 million light-years. But here's what makes it truly mysterious. The Great Attractor sits in an area of sky known as the Zone of Avoidance, a region where the dense disk of our own Milky Way blocks our view with dust and stars. We can detect its gravitational influence on thousands of galaxies. We can measure its pull on the fabric of space itself, but we cannot see what's actually there. X-ray and radio observations have revealed a massive concentration of galaxies called the Norma Cluster at the heart of the Great Attractor. But even this doesn't fully explain the immense gravitational pull. Some astronomers believe there may be something even larger beyond it, a structure so massive it pulls not just our galaxy, but the Great Attractor itself. This has led to the discovery of an even more distant gravitational anomaly called the Shapley supercluster, containing more than 8,000 galaxies and located 650 million light-years away. Our galaxy is like a leaf caught in a river, flowing toward destinations we can measure but not fully see, pulled by forces that operate on scales almost too large to comprehend. Most of the universe is invisible to us. Everything you can see, every star, every planet, every nebula glowing in the night sky, makes up less than 5% of the universe. The rest is hidden, detectable only through its gravitational effects on the matter we can observe. 27% of the universe is dark matter, a form of matter that doesn't emit, absorb, or reflect light. It doesn't interact with electromagnetic radiation at all, which means it's completely invisible. We know it exists because galaxies rotate far too quickly to be held together by the gravity of visible matter alone. Without dark matter, stars on the outer edges of galaxies would fly off into space as the galaxy spins, but they don't. Something invisible is holding them in place. Dark matter forms massive halos around galaxies, extending far beyond the visible stars and gas. These halos can be 10 times larger than the galaxy itself, creating enormous gravitational wells that trap ordinary matter and allow galaxies to form in the first place. Computer simulations show that without dark matter, galaxies as we know them could never have formed. The universe would be a very different place, perhaps just a thin gruel of gas with no stars at all. Scientists have proposed many candidates for dark matter particles. WIMPs, or weakly interacting massive particles, were long considered the leading candidate, hypothetical particles that rarely interact with ordinary matter. But despite decades of experiments in deep underground laboratories, WIMPs have never been detected. Another candidate is the axion, a theoretical particle billions of times lighter than an electron. Sterile neutrinos, primordial black holes, and even modifications to our understanding of gravity have all been proposed. The truth is, we simply don't know what dark matter is made of, and this represents one of the deepest mysteries in modern physics. The remaining 68% of the universe is something even stranger: dark energy, an unknown form of energy that permeates all of space and causes the expansion of the universe to accelerate. We'll return to this mystery later, but for now simply know that everything we can see and touch and measure directly represents only a tiny fraction of what the universe actually contains. We are islands of light in an ocean of darkness. The universe has a hole that shouldn't exist. In the cosmic microwave background, the faint afterglow of the Big Bang that fills all of space, there exists a cold spot that defies explanation. Discovered in 2004 by astronomers analyzing data from the Wilkinson Microwave Anisotropy Probe, this region is about 0.007 degrees Celsius cooler than its surroundings and spans roughly 1.8 billion light-years across. That might not sound like much of a temperature difference, but in the otherwise remarkably uniform cosmic microwave background, it stands out like a canyon in a flat plain. The cosmic microwave background is the oldest light in the universe. Radiation that has been traveling through space for 13.8 billion years since the moment the universe became transparent to light. Just 380,000 years after the Big Bang. This ancient light shows us what the infant universe looked like, and it's astonishingly smooth with temperature variations of only a few millionths of a degree. These tiny variations represent the seeds of all cosmic structure, the slight density differences that would eventually grow into galaxies and clusters. But the cold spot is different. It's about 70 microkelvins colder than the average temperature and 10 times larger than would be expected from the standard cosmological models. Several explanations have been proposed. The most conventional suggests that the cold spot is simply a statistical fluke, an unlikely but not impossible random fluctuation. The probability of such a feature occurring by chance is roughly 1 in 50, low but not impossibly so. Another explanation involves a cosmic void, an enormous region of space containing very few galaxies. As the cosmic microwave background photons travel through such a void, they would lose energy due to an effect called the integrated Sachs-Wolf effect, appearing cooler when they reach us. Surveys have indeed found evidence of an unusually large void in that direction, dubbed the Eridanus supervoid, containing about 10,000 fewer galaxies than expected. But some calculations suggest even this enormous void isn't quite large enough to fully explain the cold spot's properties. More exotic explanations venture into speculative territory. Some physicists have suggested the cold spot could be evidence of a collision between our universe and another universe in a multiverse scenario, a sort of cosmic bruise left over from the impact. Others propose it could be a topological defect in the fabric of space-time, a remnant from a phase transition in the early universe. These ideas remain highly speculative and lack supporting evidence, but they illustrate just how puzzling this feature is. The cold spot remains one of the most intriguing anomalies in cosmology, a cold mystery in the ancient light of creation. Invisible threads connect all galaxies in a cosmic web. The universe is not a random scattering of galaxies through space. Instead, galaxies are arranged in an enormous web-like structure, connected by filaments of dark matter and separated by vast voids where almost nothing exists. This cosmic web is the largest known structure in the universe, and it shapes everything from the formation of galaxies to the evolution of the cosmos itself. The filaments of the cosmic web are enormous, stretching hundreds of millions of light-years through space. They contain most of the universe's galaxies, which cluster along these threads like dew on a spider's web. Where filaments intersect, you find massive galaxy clusters containing thousands of galaxies bound together by gravity. Between the filaments lie cosmic voids, vast regions of space that contain very few galaxies and make up about 80% of the universe's volume. Some of these voids span over 300 million light-years across, regions so empty that if you were somehow transported to the center of one, you might see no galaxies at all in any direction. Just endless darkness punctuated by the faint glow of the cosmic microwave background. The cosmic web began forming in the early universe as dark matter clumped together under its own gravity. In the first few hundred million years after the Big Bang, tiny variations in the density of dark matter began to grow. Denser regions attracted more matter, becoming denser still, while less dense regions lost matter and became voids. Ordinary matter, hydrogen and helium gas, fell into the gravitational wells created by dark matter, forming the first stars and galaxies along the filaments. We can trace the cosmic web through several methods. Galaxy surveys map the three-dimensional positions of millions of galaxies, revealing the web's structure directly. Gravitational lensing, where light from distant objects is bent by intervening mass, allows us to map the distribution of dark matter itself. And observations of distant quasars show how their light is absorbed by intervening gas, tracing the filaments between galaxies. One of the most remarkable aspects of the cosmic web is that it looks strikingly similar to neural networks in the human brain or mycelial networks of fungi spreading through soil. The similarity is likely coincidental, arising from the mathematics of network growth and optimization. But it's a beautiful reminder of how patterns repeat at vastly different scales throughout nature. The cosmic web continues to evolve today as gravity pulls galaxies along filaments toward the densest nodes. Our own Milky Way sits on a minor filament, drifting slowly toward the denser regions of our local supercluster. Understanding this cosmic architecture helps us understand not just where galaxies are, but how they formed, how they evolve, and what the ultimate fate of the universe might be. Mysterious signals arrive from across the cosmos. Beginning in 2007, astronomers began detecting brief, intense bursts of radio waves from deep space. These fast radio bursts, or FRBs, last only milliseconds. But in that fleeting moment, they release as much energy as the sun emits in several days. They arrive without warning from random directions across the sky, and most appear to come from billions of light-years away, from distant galaxies in the far reaches of the observable universe. The first fast radio burst, designated FRB 010724, was discovered in archived data from the Parkes Radio Telescope in Australia. Astronomer Duncan Lorimer found the signal while analyzing observations from 2001, giving rise to the nickname Lorimer Burst. At first, many astronomers were skeptical, wondering if the signal might be terrestrial interference or an instrument malfunction. But as more bursts were discovered at different telescopes around the world, it became clear these were real cosmic phenomena. What makes fast radio bursts so mysterious is their brevity and power. The bursts last anywhere from a fraction of a millisecond to a few milliseconds at most. To produce such a brief pulse, the source must be incredibly compact, likely no larger than a few hundred kilometers across. Yet the energy released is enormous, equivalent to the total energy output of hundreds of millions of stars compressed into a few milliseconds. The dispersion of the radio waves tells us these bursts travel through ionized plasma on their journey to Earth, passing through the matter between galaxies and allowing us to estimate their distance. Most FRBs appear to originate from galaxies billions of light-years away, making them among the most luminous radio events known. For years, all detected FRBs appeared to be one-time events, single bursts never to repeat, making them nearly impossible to study in detail. Then, in 2015, astronomers discovered FRB 121102, a repeating source that has produced dozens of bursts over subsequent years. This breakthrough allowed astronomers to pinpoint its location to a small dwarf galaxy, 3 billion light-years away, and study its properties in detail. Since then, several other repeating FRBs have been found, though they remain the minority. The nature of fast radio bursts remains hotly debated. The leading explanation involves magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. These objects could produce FRBs through sudden rearrangements of their magnetic fields or through interactions between their intense magnetic fields and surrounding plasma. In 2020, a magnetar in our own galaxy produced a burst remarkably similar to extragalactic FRBs, providing strong evidence for this connection. However, magnetars may not explain all FRBs, particularly the repeating ones which show complex patterns. Other proposed explanations include collisions between neutron stars, emissions from black holes, or even more exotic phenomena. A small minority of scientists have even suggested advanced alien civilizations might produce such signals, though this remains pure speculation without supporting evidence. Fast radio bursts have become a new tool for studying the universe itself. By analyzing how the radio waves are dispersed as they travel through intergalactic space, astronomers can probe the distribution of matter between galaxies, weighing the universe and mapping the cosmic web in new ways. These brief flashes of radio light are helping illuminate the dark spaces between the stars. Billions of worlds drift through darkness without stars. Not all planets orbit stars. Scattered throughout the galaxy are countless rogue planets, worlds that either formed independently or were ejected from their original solar systems, now wandering through interstellar space in eternal darkness. These orphaned worlds receive no warmth from a nearby star, no light to mark the passage of days. They drift in perpetual night, heated only by their internal heat and the faint radiation of distant stars. Rogue planets are difficult to detect because they emit almost no light and produce no heat signature detectable from Earth. Most have been discovered through gravitational microlensing, a technique that detects the brief brightening of a distant star when a massive object passes between us and that star, bending its light through gravity. These events last only a few hours or days, giving astronomers a brief window to detect these dark wanderers. Statistical studies based on microlensing surveys suggest there may be billions or even trillions of rogue planets in our galaxy alone, possibly outnumbering stars. Some estimates suggest there could be 2 Jupiter-mass rogue planets for every star in the Milky Way, implying a vast population of unseen worlds drifting through the darkness between stellar systems. How do planets become rogues? There are 2 main formation scenarios. Some rogue planets may form just like stars, from the collapse of gas clouds in space, but never accrete enough mass to ignite fusion in their cores. These would technically be sub-brown dwarfs rather than true planets, but the distinction becomes semantic. Others are born in planetary systems, but later ejected through gravitational interactions. In the chaotic early days of a solar system, young planets migrate inward and outward, sometimes coming close enough to each other that gravitational interactions fling one planet out of the system entirely. This may have happened in our own solar system. Some models of solar system formation suggest there may have once been an additional ice giant planet that was ejected in the distant past, its gravitational influence setting the current planets into their observed orbits. That long-lost world could still be drifting through the galaxy, carrying with it frozen oceans and perhaps even ancient microbial life preserved in ice. The surface of a rogue planet would be one of the most alien environments imaginable. Without a star, the surface would be frozen, possibly reaching temperatures just a few dozen degrees above absolute zero. Any atmosphere would long ago have frozen and fallen to the surface as snow. The sky would be utterly black except for the faint light of distant stars, never rising or setting, never changing position, just an eternal star field slowly shifting over millions of years as the planet moves through the galaxy. But beneath the frozen surface, some rogue planets might harbor liquid water. If a planet is massive enough, radioactive decay in its core and residual heat from its formation could maintain a subsurface ocean beneath kilometers of ice, similar to the moons Europa and Enceladus in our own solar system. These hidden oceans could potentially support life, creating ecosystems powered not by sunlight but by chemical energy from hydrothermal vents on the ocean floor. Such life would exist in complete isolation from the rest of the galaxy, evolving in the dark waters of a wandering world. Some scientists have speculated that rogue planets might serve as interstellar arcs, carrying life between star systems over millions of years, spreading biology across the galaxy through a process called lithopanspermia. While highly speculative, this idea highlights how rogue planets blur the line between worlds and spacecraft, between home and journey. We are only beginning to understand these dark wanderers and what role they might play in the cosmic story. Some stars escape galaxies at millions of miles per hour. In the outskirts of our galaxy, astronomers have discovered stars moving so fast they will eventually escape the Milky Way entirely, achieving speeds of over 1 million miles per hour relative to the galactic center. These hypervelocity stars are racing through space at velocities that seem impossible, and the mechanisms that accelerate them reveal some of the most violent processes in the cosmos. The first hypervelocity star was discovered in 2005 by astronomer Warren Brown and his colleagues. Designated SDSS J090745, this star is traveling at over 1.5 million miles per hour, fast enough to escape the Milky Way's gravity entirely. Since then, dozens more have been found, and statistical studies suggest there may be thousands of such stars in our galaxy, all racing toward the intergalactic void. What could accelerate a star to such tremendous speeds? The leading explanation involves the supermassive black hole at the center of our galaxy. When a binary star system, two stars orbiting each other, wanders too close to this black hole, the intense gravitational field can tear the pair apart. One star is captured into orbit around the black hole, while the other is flung outward at incredible speed, like a stone from a slingshot. This process, called the Hills mechanism, after astronomer Jack Hills, who first proposed it, can accelerate stars to well over the escape velocity of the galaxy. The captured star may eventually spiral into the black hole, while its companion races toward the galactic edge, carrying with it the memory of its lost partner. Other mechanisms can also produce hypervelocity stars. Supernova explosions in binary systems can kick the surviving star to high velocities. When a massive star explodes as a supernova, the sudden loss of mass can unbind the binary system, sending the companion star flying off at high speed. Three-body interactions in dense star clusters can also produce high-velocity ejections, though these typically don't reach true hypervelocity speeds. Some hypervelocity stars may come from outside our galaxy entirely. The Large Magellanic Cloud, a satellite galaxy of the Milky Way, has its own supermassive black hole that could eject stars. Some of these stars might end up in the Milky Way, immigrants from another galaxy traveling at speeds that betray their violent origins. The existence of hypervelocity stars has profound implications for galactic evolution. These stars carry heavy elements forged in stellar cores out into intergalactic space, potentially enriching the gas between galaxies and seeding future generations of star formation. If any of these stars have planets, those worlds would experience one of the strangest journeys imaginable, beginning their existence in a galaxy teeming with stars and eventually finding themselves in the vast emptiness of intergalactic space, where the night sky holds only distant, fuzzy patches of light from receding galaxies. For any inhabitants of such a world, if such beings could exist, the universe would appear to be emptying around them, the stars of their home galaxy falling behind, while the stars of neighboring galaxies remain forever out of reach. They would be cosmic voyagers on a one-way journey into the growing darkness between galaxy clusters. And now we drift deeper into the cosmos, toward the darkest and most extreme objects in the universe, regions where the laws of physics are stretched to their breaking point and space-time itself becomes strange. Let us turn our attention to black holes, those mysterious gravitational prisons from which not even light can escape, and explore the profound mysteries that surround them. Black holes trap information forever, and this breaks physics. One of the deepest paradoxes in modern physics emerges when we combine two of our most successful theories, quantum mechanics and general relativity, and apply them to black holes. According to quantum mechanics, information cannot be destroyed. This principle, known as unitarity, is fundamental to how quantum physics works. Every process in quantum mechanics must be reversible in principle, meaning information about the initial state can always be recovered from the final state. but black holes seem to violate this rule. When anything falls into a black hole, it crosses the event horizon and is lost forever from our universe. All information about that object, its structure, its quantum state, everything, appears to be permanently erased. This is the black hole information paradox, first identified by Stephen Hawking in the 1970s, and it remains one of the most profound unsolved problems in theoretical physics. The paradox deepens when we consider Hawking radiation. Hawking showed that black holes are not completely black. Through a quantum mechanical process near the event horizon, they emit thermal radiation and slowly evaporate. Virtual particle pairs, matter and antimatter, constantly appear and annihilate near the event horizon. Occasionally, one particle falls into the black hole while the other escapes, and to an outside observer, this appears as radiation coming from the black hole. This Hawking radiation carries energy away, meaning the black hole gradually loses mass and shrinks. Eventually, after an incomprehensibly long time, a stellar mass black hole would evaporate completely, much longer than the current age of the universe. But here's the problem. Hawking radiation is thermal, meaning it's completely random and carries no information about what fell into the black hole. If a black hole evaporates completely into random thermal radiation, all the information about everything that ever fell in would be permanently destroyed, violating quantum mechanics. Imagine throwing an encyclopedia into a black hole, then waiting for it to evaporate. The Hawking radiation that emerges would be no different than if you had thrown in a pile of random atoms with the same total mass. The knowledge in the encyclopedia would be gone from the universe forever. Many solutions have been proposed. Some physicists suggest the information is somehow encoded in the Hawking radiation in subtle correlations we don't yet understand. Others propose that information is stored on the event horizon itself, consistent with the holographic principle which suggests all information about a volume of space can be encoded on its boundary. More radical ideas suggest black holes might leave behind remnants after they evaporate, tiny, stable objects that preserve the lost information, or that information might leak out through wormholes to other universes or other regions of space-time. Some physicists have proposed that the event horizon itself might be a seething firewall of high-energy particles that would destroy anything trying to cross, though this contradicts general relativity's prediction that nothing special should happen at the horizon. The paradox has inspired decades of theoretical work and led to profound insights about the nature of space-time, quantum mechanics, and the deep connections between them. It suggests that our current understanding of physics is incomplete, and that a full theory of quantum gravity will be needed to resolve the puzzle. For now, the mystery remains. When something crosses the event horizon of a black hole, we simply don't know what happens to the information it carried, and this gap in our understanding points toward something fundamental we have yet to discover about the universe. Black holes are not completely black. For most of history, astronomers believed that once something fell into a black hole. It could never escape. The gravitational pull becomes so strong beyond the event horizon that even light, traveling at the fastest possible speed, cannot break free. Black holes seemed to be one-way destinations, cosmic traps that only grew larger as they consumed more matter. But in 1974, Stephen Hawking made a discovery that changed everything. He showed through a remarkable combination of quantum mechanics and general relativity that black holes actually emit radiation. a faint thermal glow coming from near the event horizon. This radiation, now called Hawking radiation, means black holes are not truly black after all. They slowly leak energy, and over immense timescales, they evaporate. The process works through the strange quantum mechanical properties of empty space. Vacuum is not truly empty, but seethes with virtual particles, particle-antiparticle pairs that constantly pop into existence and immediately annihilate. Near the event horizon of a black hole, something remarkable happens. A virtual pair appears right at the boundary. One particle falls into the black hole while the other escapes. To a distant observer, it appears that the black hole has emitted a particle. But energy must be conserved. The escaping particle has positive energy, so the particle that fell in must have negative energy from the black hole's perspective. This negative energy particle reduces the black hole's mass slightly. Repeated over and over, this process causes the black hole to gradually lose mass and shrink. The effect is extraordinarily weak for large black holes. A black hole with the mass of our Sun would have a temperature of only 60 nanokelvins, far colder than the cosmic microwave background, meaning it would actually gain more energy from absorbing background radiation than it loses through Hawking radiation. Such a black hole would take 10 to the 67 years to evaporate, an unimaginably long time, far longer than the current age of the universe, which is only about 10 to the 10 years. But smaller black holes evaporate faster. The temperature of Hawking radiation is inversely proportional to the black hole's mass, so smaller black holes are hotter. A black hole the mass of a mountain would be about room temperature. A black hole the mass of an aircraft carrier would glow white hot. And a black hole the mass of a large ship would be as hot as the surface of the Sun. As a black hole evaporates, it gets smaller, hotter, and evaporates faster, leading to a runaway process. In its final moments, a black hole would release a tremendous burst of energy. A small primordial black hole, if any exist, ending its life today would explode with the energy of millions of nuclear weapons. Some physicists have even suggested we might detect such explosions if primordial black holes exist in our cosmic neighborhood. Hawking radiation has profound implications. It shows that black holes have a temperature and entropy, connecting thermodynamics with gravity in unexpected ways. It suggests deep links between quantum mechanics, gravity, and information theory. And it means that black holes, those seemingly eternal objects, are actually temporary, destined to eventually return their borrowed energy to the universe in a final flash of light. The universe has black holes of every size, and we have no idea how. Black holes come in a remarkable range of sizes, from microscopic to billions of times the mass of our Sun, and the full spectrum of black hole masses presents one of astronomy's most persistent mysteries. We understand reasonably well how stellar mass black holes form, but the extremes of the black hole population remain deeply puzzling. Stellar mass black holes form when massive stars explode as supernovae at the end of their lives. If the core is massive enough, typically more than about 25 times the Sun's mass, it collapses directly into a black hole. These stellar remnants typically range from about 5 to several dozen solar masses. We've detected many such black holes in our galaxy, often because they're part of binary systems where they pull matter from a companion star, creating bright X-ray sources as the infalling material heats up. At the other extreme lie supermassive black holes, monsters containing millions or billions of solar masses. residing at the centers of most large galaxies. Our own Milky Way harbors Sagittarius A star, a supermassive black hole containing about 4 million times the Sun's mass. The largest known supermassive black holes exceed 20 billion solar masses, containing as much mass as an entire small galaxy of stars compressed into a region smaller than our solar system. Here's the mystery. We have no clear explanation for how supermassive black holes formed, especially the ones that existed when the universe was very young. Astronomers have found quasars, galaxies with actively feeding supermassive black holes that existed less than a billion years after the Big Bang. These black holes already contained millions or even billions of solar masses, but there simply wasn't enough time for them to grow from stellar mass seeds through normal accretion. A black hole grows by pulling in surrounding gas and stars, but there are limits to how fast this can happen. As matter falls toward a black hole, it heats up and emits radiation. This radiation pushes outward on infalling material, creating a feedback effect that limits how quickly the black hole can grow. This is called the Eddington limit. Even growing at the maximum possible rate, a stellar mass black hole formed from the first stars could not have grown to a billion solar masses in the time available. Several solutions have been proposed. Perhaps supermassive black holes formed directly from the collapse of enormous gas clouds in the early universe, bypassing the stellar stage entirely. These direct collapse black holes could have been born with thousands or even hundreds of thousands of solar masses, giving them a head start. Or perhaps the first generation of stars were far more massive than anything we see today. Hundreds or even thousands of solar masses, creating much larger seed black holes when they died. Another mystery involves intermediate mass black holes, those between about 100 and 100,000 solar masses. For many years, these remained elusive. We knew about stellar mass black holes and supermassive black holes, but the gap between them was puzzling. If supermassive black holes grow from smaller seeds, where are the intermediate stages? Recently, evidence for intermediate mass black holes has begun to accumulate. Dense star clusters called globular clusters may harbor them at their centers. Some ultraluminous X-ray sources, extremely bright X-ray emitters in nearby galaxies, appear to be intermediate mass black holes. And gravitational wave detections have revealed mergers producing black holes in this mass range. But we still don't understand the full picture of black hole formation across all masses. Do all supermassive black holes grow from smaller seeds, or can they form directly? Why are intermediate mass black holes apparently less common than their smaller and larger cousins? These questions remain at the frontier of astrophysics. Time stops at the edge of a black hole. One of the strangest properties of black holes emerges directly from Einstein's general relativity, the prediction that gravity affects the flow of time itself. The stronger the gravitational field, the slower time passes relative to regions of weaker gravity. Near a black hole, this effect becomes extreme. At the event horizon, from the perspective of a distant observer, time appears to stop completely. Imagine watching a spacecraft fall toward a black hole. As it approaches the event horizon, you would see it slow down. The light from the spacecraft would become redder as photons lose energy climbing out of the deep gravitational well. The spacecraft's clock would appear to tick slower and slower. The crew would seem to move in slow motion, their signals arriving less and less frequently and increasingly redshifted. As the spacecraft reached the event horizon, from your perspective it would appear to freeze, taking forever to cross that final boundary. The last light from the spacecraft would be redshifted into radio waves, microwaves, and eventually become undetectable. But from the crew's perspective, assuming they could somehow survive the tidal forces, nothing special would happen at the event horizon. They would cross it in finite time according to their own clocks, passing the point of no return without any local indication that something significant had occurred. Time would flow normally for them. This difference in perspectives is one of the most profound aspects of relativity. The experience of time depends on your reference frame, on your motion, and on the strength of gravity where you are. There is no universal clock ticking away the same for everyone everywhere. Near black holes, these effects become dramatic. This time, dilation has practical implications for anything near a black hole. If you could somehow orbit close to a black hole's event horizon and return to a safe distance, you would find that far less time had passed for you than for someone who remained far away. You could orbit for what feels like a few hours and return to find years or decades had passed for distant observers. This isn't science fiction. It's a consequence of general relativity verified by countless experiments and observations. GPS satellites must account for tiny relativistic time dilation effects to maintain accurate positioning. The principle is well established. Black holes just take it to an extreme. The time dilation near black holes also affects what we see when matter falls in. As gas spirals toward a black hole, time dilation causes the inner regions to appear to evolve more slowly. X-ray variability from close to the event horizon happens on timescales stretched by gravitational time dilation, creating observable signatures that astronomers use to map regions close to black holes. For rotating black holes, effects become even stranger. A spinning black hole drags space-time around with it, creating a region called the ergosphere where nothing can remain stationary. Space itself is being pulled around the black hole. Inside the ergosphere but outside the event horizon, time and space become partially intertwined. One of the spatial directions becomes time-like, meaning you would be forced to move in that direction just as you are forced to move forward in time. You couldn't resist this motion any more than you can stop time from passing. These bizarre properties make black holes natural laboratories for testing general relativity under the most extreme conditions. Regions where space-time becomes twisted and time itself flows at different rates for different observers. Black holes can spin, and this changes everything. Not all black holes are the same. While mass determines the strength of a black hole's gravity, another property shapes the space around it in profound ways. Black holes can rotate, spin at tremendous speeds, and this rotation dramatically alters their properties and the space-time around them. A rotating black hole is described by the Kerr metric, named after physicist Roy Kerr, who found the solution in 1963. Unlike a non-rotating or Schwarzschild black hole, which is perfectly spherical with a simple event horizon, a rotating black hole is flattened at the poles and bulges at the equator. The event horizon is no longer spherical but oblate, shaped like a squashed sphere. Outside the event horizon lies a region unique to rotating black holes called the ergosphere. Inside the ergosphere, space-time is dragged around by the black hole's rotation so powerfully that nothing can remain stationary. Everything must rotate in the same direction as the black hole, carried along by the dragging of space-time itself. This frame-dragging effect, also called the lens-Thirring effect, extends beyond the ergosphere, but is strongest near it. The ergosphere touches the event horizon at the poles but extends farther out at the equator. Between the ergosphere and the event horizon lies a region where strange things become possible. A process called the Penrose process allows energy to be extracted from a rotating black hole. If an object enters the ergosphere and splits into two pieces, with one piece falling into the black hole with negative energy and angular momentum, while the other escapes, the escaping piece can have more energy than the original object. The black hole loses rotational energy in the process, slowing down slightly. This isn't just theoretical. Some astrophysicists believe this mechanism might power some of the most energetic phenomena in the universe. Jets of matter and energy that shoot from near black holes at nearly the speed of light, extending for thousands of light years through space, might be powered by the rotational energy of spinning black holes. These jets carry enormous amounts of energy, sometimes outshining the entire galaxy that hosts the black hole. The material in these jets is moving at over 99% of light speed, and the total energy involved can exceed the output of billions of stars. Rotating black holes can spin at incredible rates. The maximum rotation rate occurs when the event horizon is spinning at the speed of light at its equator. Such a maximally rotating black hole would have its event horizon and ergosphere nearly coincide, creating a region where space-time is twisted to the extreme. Most black holes probably rotate at substantial fractions of this maximum rate. When black holes form from collapsing stars, they inherit the angular momentum of the stellar core. When they grow by accreting matter, they gain angular momentum from the infalling material. And when black holes merge, the final black hole spins at a rate determined by the masses and spins of the progenitors. Observations of X-rays from matter orbiting close to black holes allow astronomers to measure their spin rates. Some supermassive black holes appear to be spinning at more than 90% of the maximum possible rate, whirling around hundreds of times per second, despite containing millions of solar masses. The spin of black holes affects the orbits of nearby objects in complex ways. Close to a rotating black hole, there exist no stable circular orbits, only complex orbital paths that precess and evolve. Light itself can be captured in unusual orbits, spiraling around the black hole multiple times before escaping or falling in. When two black holes merge, their spins affect the gravitational waves produced and the properties of the final black hole. LIGO and other gravitational wave observatories measure these effects, allowing astronomers to determine not just the masses of merging black holes, but also their spins. This provides crucial information about how black holes form and evolve. Inside the event horizon of a rotating black hole, the structure becomes even stranger than for a non-rotating one. Instead of a point singularity, a rotating black hole has a ring singularity, a circular region of infinite density. Hypothetically, if you could survive crossing the event horizon of a rapidly spinning black hole, you might pass through the ring singularity into a different region of space-time, though this remains purely theoretical, and the real behavior under such extreme conditions is unknown. Black holes collide and ripple space-time itself. On September 14, 2015, humanity detected something that had never been observed before. At two facilities separated by thousands of miles, ultra-sensitive instruments measured a tiny vibration in space-time itself, a gravitational wave that had traveled across the universe for over 1 billion years before reaching Earth. This signal came from two black holes, each about 30 times the mass of the Sun, that had spiraled together and merged into a single larger black hole in a catastrophic collision. The detection opened an entirely new way of observing the universe and confirmed a prediction Einstein made a century earlier. Gravitational waves are ripples in the fabric of space-time, propagating outward at the speed of light from any accelerating mass. Einstein's general relativity predicted their existence, but he thought they would be far too weak to ever detect. For most astronomical events, he was right. Even massive objects like planets and stars produce gravitational waves far too faint to measure. But black hole mergers are different. As two black holes spiral together in the final moments before merger, they orbit each other at a significant fraction of light speed. The orbital period in the last second before merger drops from tens of times per second to hundreds of times per second. During this final spiral, called the chirp, the black holes convert an enormous amount of mass into gravitational wave energy through Einstein's famous equation E equals mc squared. In a fraction of a second, a merging black hole system can emit more power in gravitational waves than all the stars in the observable universe combined emit in light. The amount of mass converted to energy can be several times that of the Sun, vanishing from the universe in the form of space-time ripples. These waves stretch and squeeze space itself as they pass. When a gravitational wave passes through you, you are alternately stretched and compressed in perpendicular directions by a tiny amount. The LIGO detectors measure this effect using laser interferometry. Two arms, each 4 kilometers long and perpendicular to each other, contain laser beams bouncing between mirrors. When a gravitational wave passes through, one arm becomes slightly longer while the other becomes slightly shorter, changing the interference pattern of the reunited laser beams. The sensitivity is astonishing. LIGO can detect changes in the arm length smaller than 1/10,000th of the diameter of a proton. It's like measuring the distance to the nearest star to the width of a human hair. Achieving this sensitivity required isolating the mirrors from every possible source of vibration, from seismic noise to passing trucks to quantum fluctuations in the laser light itself. Since that first detection, gravitational wave observatories have detected dozens of black hole mergers, along with neutron-star mergers and other exotic events. Each detection provides information about the masses and spins of the merging objects, the distance to the merger, and even tests of general relativity under the most extreme conditions. The observations have revealed surprises. Black holes merge more frequently than many predicted. They exist in a wider range of masses than expected. Some mergers involve black holes much more massive than anything previously known from X-ray observations. And the population of black holes revealed by gravitational waves is teaching us about stellar evolution, supernova physics, and the history of star formation throughout cosmic time. Gravitational waves also provide a new way to study the universe itself. Because these waves pass through matter almost completely unaffected, they carry information from the merger unchanged. Unlike light, which can be absorbed or scattered, gravitational waves from a merger reach us directly, allowing us to observe events that would be invisible in any other way. Future gravitational wave observatories will be even more sensitive. Space-based detectors like LISA, planned for the next decade, will detect lower-frequency gravitational waves from supermassive black hole mergers, opening another window on the universe. These mergers involve black holes millions or billions of times the mass of the Sun and produce gravitational waves with periods of minutes to hours rather than milliseconds. The gravitational wave universe is vast and varied, and we are only beginning to explore it. every detection provides another glimpse into the most violent and energetic events in the cosmos, where black holes collide and space-time itself rings like a bell. Magnetars twist space-time with impossible magnetic fields. Neutron stars are already among the strangest objects in the universe. When a massive star explodes as a supernova, if its core is not quite massive enough to collapse into a black hole, it becomes a neutron star, an object containing 1 to 2 times the Sun's mass compressed into a sphere only about 20 kilometers across. The density is almost beyond comprehension. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. But some neutron stars are stranger still. Magnatars are neutron stars with magnetic fields thousands of times stronger than those of ordinary neutron stars, reaching intensities of 10 to the 15th Gauss, about 1 quadrillion times stronger than Earth's magnetic field. These are the strongest magnetic fields known to exist in the universe, and their effects are extraordinary. The magnetic field of a magnetar is so intense it warps the shape of atoms. Atoms are mostly empty space with a tiny nucleus surrounded by an electron cloud. In a normal environment, atoms are roughly spherical. But in a magnetar's magnetic field, atoms are stretched into elongated needle shapes, with their electron clouds squashed perpendicular to the magnetic field and extended parallel to it. The chemistry and physics of matter in such fields is completely different from anything we experience. If you somehow found yourself 1,000 kilometers from a magnetar, the magnetic field would be strong enough to be lethal. It would disrupt the electrical activity in your nervous system and start to tear apart the molecular bonds in your body. At closer distances, matter itself becomes impossibly strange. The magnetar would warp space-time around itself through the sheer energy density of its magnetic field, not just through its mass, but through the energy stored in magnetism itself. This is a prediction of general relativity. Energy and mass are equivalent, and concentrated energy can curve the space-time just as mass does. Magnetars power some of the most energetic transient events in astronomy. Occasionally, a magnetar's magnetic field becomes unstable and suddenly rearranges itself, a magnetic equivalent of an earthquake called a starquake. The solid crust of the neutron star cracks and shifts, and energy stored in the magnetic field is suddenly released. In a fraction of a second, a magnetar can emit as much energy as the Sun produces in tens of thousands of years. This energy emerges as X-rays and gamma rays, and in rare cases can be detected even from magnetars in distant galaxies. On December 27, 2004, a giant flare from magnetar SGR 1806-20 literally knocked electrons out of Earth's upper atmosphere, despite the magnetar being 50,000 light-years away on the far side of our galaxy. For 1/10 of a second, this object, only 20 kilometers across, emitted more energy than all the stars in the Milky Way combined. The radiation hit Earth's night side, disrupting satellites and triggering radiation sensors. If such a flare occurred from a magnetar just 10 light-years away, it could potentially cause a mass extinction on Earth through radiation damage. Fortunately, no known magnetars are that close. The origin of magnetars' extreme magnetic fields remains somewhat mysterious. The leading theory suggests they form from massive stars that already had strong magnetic fields. When the core collapses to form a neutron star, the magnetic field is compressed and intensified. Conservation of magnetic flux, a principle similar to conservation of angular momentum, means the field strength increases dramatically as the star shrinks. But this may not fully explain the strongest magnetars, suggesting additional mechanisms might amplify fields even further. Magnetars are thought to be young objects, only thousands to tens of thousands of years old. Their extreme magnetic fields decay over time as the field energy is gradually radiated away. Eventually, after perhaps 10,000 to a million years, a magnetar's field weakens enough that it becomes indistinguishable from an ordinary neutron star. This means magnetars represent a brief but spectacular phase in the life of certain neutron stars, cosmic monsters that shine brilliantly in X-rays before fading into relative quiet. The universe holds pulsars that keep time better than atomic clocks. Some neutron stars spin, and they spin fast. When a massive star collapses to form a neutron star, conservation of angular momentum means the neutron star rotates rapidly, just as a figure skater spins faster when pulling their arms inward. The fastest known pulsars rotate over 700 times per second, spinning faster than a kitchen blender despite containing more mass than the sun. These objects are called pulsars because they emit beams of radiation from their magnetic poles, and as the neutron star rotates, these beams sweep across space like lighthouse beams. If Earth happens to lie in the path of the beam, we detect a pulse of radio waves, or sometimes X-rays, with each rotation. The timing of these pulses can be extraordinarily regular, keeping better time than the best atomic clocks humanity has built. The regularity of pulsar pulses is astonishing. The best pulsars vary by less than a few microseconds over years of observation. They are so regular that astronomers use them as cosmic clocks. An array of precisely timed pulsars spread across the sky can even be used to detect gravitational waves, with the waves causing tiny variations in the pulse arrival times in a correlated pattern across multiple pulsars. This technique, called pulsar timing arrays, is sensitive to gravitational waves with periods of months to years, filling a gap between the frequencies accessible to ground-based detectors like LIGO and future space-based detectors. Pulsars gradually slow down as they age, losing rotational energy to the emission of radiation and sometimes to winds of particles flowing off the neutron star. By measuring how quickly a pulsar is slowing, astronomers can estimate its age and the strength of its magnetic field. Young pulsars, hundreds to thousands of years old, typically have the strongest magnetic fields and emit the most energetic radiation. Old pulsars, millions of years old, rotate more slowly and have weaker fields, but some pulsars have been spun up to extremely fast rotation rates through a recycling process. If a neutron star has a companion star in a binary system, it can pull matter from that companion. As this matter spirals inward, it carries angular momentum that spins up the neutron star, increasing its rotation rate. These millisecond pulsars, rotating hundreds of times per second, are the end result of this process. They have relatively weak magnetic fields because their fields have had time to decay, but they spin incredibly fast, creating some of the most precisely regular signals in nature. The discovery of pulsars in 1967 by Jocelyn Bell and Anthony Hewish was initially so puzzling that the signals were jokingly referred to as LGM-1 for little green men, because the regularity seemed almost artificial. The true explanation, rotating neutron stars with beamed emission, is arguably more remarkable than aliens. It reveals that nature can create objects of such extreme density and regularity that they function as cosmic precision instruments. Pulsars have taught us about the equation of state of matter at nuclear densities, the physics of strong magnetic fields, the the dynamics of binary star systems and even provided some of the first evidence for gravitational waves years before LIGO's direct detections. When binary pulsars, systems containing two neutron stars orbiting each other, were discovered and precisely timed over many years, astronomers found the orbital period was decreasing at exactly the rate predicted by general relativity if the system was losing energy to gravitational waves. This indirect detection of gravitational waves earned the Nobel Prize decades before the waves were directly measured. In the quiet sweep of pulsar beams across the galaxy, we find some of nature's most precise timepieces, cosmic metronomes that mark the passage of time with incredible fidelity. The universe produces explosions that dwarf supernovae. Supernovae represent the deaths of massive stars, explosions so bright they can outshine an entire galaxy for weeks. But there exist even more powerful explosions in the universe, events that release more energy in a few seconds than the sun will emit in its entire 10 billion-year lifetime. These are gamma-ray bursts, the most energetic electromagnetic events known to occur. Gamma-ray bursts were discovered accidentally in the late 1960s by satellites designed to detect nuclear weapons tests. Instead of nuclear explosions, they found bursts of gamma rays coming from space, brief flashes lasting from milliseconds to several minutes. For decades, their origin remained mysterious. Were they nearby or distant? What could produce such intense bursts of high-energy radiation? The breakthrough came in the 1990s when astronomers managed to quickly locate the positions of gamma-ray bursts and observe them with other telescopes. The bursts were found to come from distant galaxies, billions of light-years away. This meant they were extraordinarily luminous. To be detectable at such distances, a gamma-ray burst must be releasing as much energy in a few seconds as an entire galaxy of hundreds of billions of stars emits in the same time. The numbers are staggering. A typical long-duration gamma-ray burst releases about 10 to the 51 ergs of energy, comparable to the energy released in a supernova explosion, but concentrated into gamma rays, rather than spread across the electromagnetic spectrum. This energy is released from a region only hundreds of kilometers across, creating intensities almost beyond imagination. We now understand that gamma-ray bursts come in two main types. Long bursts, lasting more than 2 seconds, are associated with the deaths of very massive stars. When certain massive stars explode as supernovae, if the core collapse produces a rapidly rotating black hole or magnetar, jets of matter and energy can be launched along the rotation axis at nearly the speed of light. These jets bore through the collapsing star and emerge into space, carrying enormous energy. If Earth happens to lie along one of these jets, we see a gamma-ray burst. Short bursts, lasting less than 2 seconds, come from the mergers of neutron stars, or from a neutron star merging with a black hole. When these compact objects spiral together, they produce gamma-ray bursts through similar jet mechanisms. The detection of gravitational waves from a neutron star merger in 2017 followed seconds later by the detection of a short gamma-ray burst from the same location, confirmed this origin. The jets in gamma-ray bursts move at velocities exceeding 99.99% of the speed of light. At such speeds, relativistic effects become extreme. The radiation is beamed forward into a narrow cone, and time dilation means the jet can appear to move faster than light as it streams toward us, though it never actually exceeds light speed. This relativistic beaming means we only see gamma-ray bursts when the jet points nearly directly at us. For every burst we detect, there may be hundreds pointing in other directions that we never see. This suggests gamma-ray bursts, or at least the events that produce them, may be relatively common in the universe, but we only notice the small fraction aimed our way. If a gamma-ray burst occurred in our galaxy and happened to be aimed at Earth, the consequences could be severe. The gamma rays would interact with Earth's atmosphere, destroying the ozone layer and potentially causing a mass extinction through increased ultraviolet radiation reaching the surface. Some scientists have proposed that past mass extinctions might have been triggered by nearby gamma-ray bursts, though evidence for this remains speculative. Fortunately, gamma-ray bursts from within our galaxy appear to be rare, perhaps occurring once every few million years, and the chance of one being aimed at Earth is very small. The universe continues to produce these titanic explosions at a rate of perhaps a few per day across the observable universe, each one marking the death of a massive star or the merger of stellar remnants, each one briefly creating the most extreme conditions of energy and density outside a black hole. They remind us that the universe is not a quiet place. It remains violent and dynamic, still echoing with the energy of creation and destruction even 13.8 billion years after the beginning. And in the glow of these distant detonations, we find clues to stellar evolution, jet physics, and the chemical enrichment of galaxies across cosmic time. We have wandered through the darkest corners of the cosmos, through black holes and magnetic monsters, and now we turn our attention to the very fabric of reality itself, to time and space and the mysterious forces that shape them. Here in the quiet darkness, let us explore the fundamental mysteries of existence, the questions that touch the deepest nature of the universe we inhabit. Time flows in only one direction, and nobody knows why. You remember the past. You experience the present. You anticipate the future. Time seems to flow inexorably forward, from yesterday to today to tomorrow, never reversing, never pausing, always moving in the same direction. This one-way flow of time is so fundamental to our experience that we rarely question it. But physics does. The laws of physics, at their most fundamental level, do not distinguish between past and future. The equations that describe gravity, electromagnetism, and even quantum mechanics work equally well whether time runs forward or backward. If you filmed most physical processes at the microscopic level and played the film backward, you would see something that obeys the laws of physics just as well as the forward version. A ball bouncing, molecules colliding, even light reflecting off a mirror, all these processes are time-reversible in principle. Yet we never see time run backward. Eggs break but never spontaneously reassemble. Coffee and cream mix but never unmix. We age but never grow younger. The arrow of time points stubbornly in one direction. Why? The answer, as far as we understand it, lies in entropy, a measure of disorder or randomness in a system. The second law of thermodynamics states that entropy always increases in a closed system. Disorder naturally grows over time. This increasing entropy gives time its direction. The past is the direction of lower entropy. The future is the direction of higher entropy. When an egg breaks, it transitions from a state of relatively low entropy, an organized structure, to a state of high entropy, scattered fragments. The reverse process, broken pieces spontaneously assembling into an intact egg, would require entropy to decrease, which, while not absolutely impossible, is so staggeringly improbable that it never happens in practice. But this explanation raises a deeper mystery. Why was the entropy of the universe so low in the past? At the moment of the Big Bang, the universe was in an extraordinarily low entropy state. highly ordered in certain ways that we still don't fully understand. All the matter and energy was compressed into a tiny region, but it was distributed very smoothly and uniformly, with only tiny variations in density. This smooth, uniform state had low gravitational entropy. As the universe expanded and evolved, gravity amplified those tiny variations, pulling matter together into clumps that became galaxies, stars, and planets. This clumping represents an increase in gravitational entropy. Stars burn, converting ordered nuclear fuel into disordered radiation and heat. Black holes form, representing high-entropy objects. The universe evolves from order to disorder, from low entropy to high entropy, and this evolution defines the arrow of time. But why did the universe begin in such a low entropy state? This is one of the deepest unsolved questions in physics. Some physicists argue it's simply an initial condition, a brute fact about how the universe began that requires no further explanation. Others suggest the low entropy beginning might be explained by the physics of cosmic inflation, a period of rapid expansion in the first fraction of a second after the Big Bang. Still, others propose that our universe might be part of a larger multiverse where different regions have different entropy states, and we find ourselves in a region with low initial entropy simply because that's the only kind of region where complex structures like stars, planets, and life can form. There are even proposals that time's arrow might reverse in distant regions of space-time or in contracting phases of a cyclic universe. The question touches on deep issues in physics, cosmology, and even philosophy. Time's arrow is intimately connected to memory, causality, and consciousness itself. We remember the past because our brains record information, increasing their entropy in the process. We cannot remember the future because memory formation is an irreversible thermodynamic process. Cause precedes effect because the universe evolves from lower to higher entropy states. In the quiet flow of moments, from past to present to future, the universe is evolving, growing more disordered, spreading its energy ever more thinly across expanding space. And in this cosmic unwinding, time finds its direction. Nothing can travel faster than light, and this shapes reality. The speed of light in vacuum, exactly 299,792,458 meters per second, is not just the speed at which light travels. It is a fundamental speed limit woven into the structure of space-time itself. Nothing with mass can reach this speed, and no information can travel faster. This cosmic speed limit has profound consequences for causality, time, space, and the very nature of reality. Einstein's special relativity, published in 1905, revealed that the speed of light is the same for all observers regardless of their motion. This seemingly simple statement has remarkable implications. If you're on a spaceship moving at half the speed of light and you shine a flashlight forward, you might expect the light to travel at 1.5 times light speed relative to someone at rest. But it doesn't. Both you and the stationary observer measure the light traveling at exactly the same speed. This constancy of light speed forces us to abandon our intuitive notions of absolute space and absolute time. Time and space become relative, dependent on the observer's motion. Moving clocks run slower. Moving rulers are contracted. These are not illusions or measurement errors, but real physical effects confirmed by countless experiments. As you approach the speed of light, relativistic effects become extreme. At 90% of light speed, time passes about 43% slower for you than for a stationary observer. At 99% of light speed, time slows by a factor of 7. At 99.9999% of light speed, time nearly stops from an external perspective. But why this particular speed? Why does the universe have this limit? The answer lies in the structure of space-time itself. Light speed is more fundamentally the speed of causality, the maximum rate at which cause and effect can propagate through space. It is the speed at which massless particles must travel, and it represents the conversion factor between space and time. In the equations of relativity, space and time are measured in compatible units related by the speed of light. The speed limit exists because space-time is a unified four-dimensional structure, and the speed of light is the exchange rate between the spatial dimensions and the time dimension. Attempting to exceed light speed leads to logical contradictions. If you could travel faster than light, you could in principle send information into your own past, creating causal paradoxes. You could receive an answer before you sent the question. Cause and effect would break down. The light speed limit protects causality, ensuring that the universe makes logical sense. Particles with mass require infinite energy to reach light speed. As you accelerate an object, its mass effectively increases from the perspective of the energy required to accelerate it further. The closer you get to light speed, the more energy is needed for each additional increment of speed. To actually reach light speed would require infinite energy, which is impossible. Only massless particles like photons can travel at light speed, and they must always travel at exactly this speed, never faster or slower. This speed limit shapes the observable universe. When we look at distant galaxies, we see them as they were billions of years ago because light from them has taken billions of years to reach us. We cannot see beyond a certain distance, about 46 billion light-years currently. Not because the universe ends there, but because light from farther regions hasn't had time to reach us yet. The expansion of space itself can exceed light speed. Distant galaxies are receding from us faster than light, carried by the expansion of space itself. This doesn't violate relativity because nothing is moving through space faster than light. Rather, space itself is stretching, increasing the distance between galaxies. An ant walking on the surface of an inflating balloon can recede from another ant faster than its walking speed simply because the balloon is expanding. For practical space travel, the light speed limit poses severe challenges. Our nearest stellar neighbor, Proxima Centauri, is 4.2 light-years away. Even traveling at a substantial fraction of light speed, a journey there would take years or decades. The center of our galaxy is 26,000 light-years distant. Andromeda, our nearest large galactic neighbor, is 2.5 million light-years away. The observable universe spans 93 billion light-years. The cosmos is vast beyond human scales, and the speed of light, while tremendously fast by everyday standards, is slow compared to cosmic distances. Some theoretical proposals attempt to circumvent the light speed limit through exotic means. Wormholes, hypothetical shortcuts through space-time, might connect distant regions without requiring faster-than-light travel. Alcubierre drives, theoretical devices that would contract space ahead of a ship and expand it behind, might move a bubble of space faster than light while nothing inside the bubble exceeds light speed locally. But all such proposals require exotic matter with negative energy density, something that may not exist or may be impossible to create in sufficient quantities. For now, and likely forever, the speed of light remains the ultimate speed limit, a cosmic constant that shapes the structure of space-time, limits how quickly information can travel, and determines the ultimate boundaries of causality and observation in our universe. Particles separated by vast distances remain mysteriously connected. In the strange realm of quantum mechanics, particles can become entangled, linked in such a way that measuring one instantly affects the other, regardless of the distance between them. This phenomenon, which Einstein famously called spooky action at a distance, has been confirmed in countless experiments and represents one of the deepest mysteries in physics. When two particles become entangled, their quantum states become correlated. Measure a property of one particle, such as its spin, and you instantly know the corresponding property of the other particle, even if it's on the other side of the galaxy. The measurement of one particle appears to instantaneously determine the state of the other, faster than light could travel between them. Einstein was deeply troubled by this. It seemed to violate the principle that nothing can travel faster than light, that no influence can propagate through space instantaneously. He argued that quantum mechanics must be incomplete, that there must be hidden variables, properties the particles possess all along that we simply don't know until we measure them. But experiments have proven Einstein wrong. In the 1960s, physicist John Bell derived inequalities that any theory based on local hidden variables must satisfy. Experiments testing Bell's inequalities have consistently violated them in exactly the way quantum mechanics predicts. The correlations between entangled particles are stronger than any theory based on predetermined properties could explain. The particles do not possess definite values for their properties before measurement. The act of measurement on one particle genuinely affects the other, instantaneously, regardless of distance. Yet this doesn't allow faster-than-light communication. When you measure an entangled particle, you get a random result. You cannot control what result you get. The correlation with the distant particle only becomes apparent when you compare the measurement results, and that comparison requires classical communication at or below light speed. You cannot use entanglement to send information faster than light, preserving causality and preventing paradoxes. Quantum entanglement is now understood as a fundamental feature of reality, not a flaw in quantum mechanics, but a genuine property of nature. It has practical applications in emerging technologies. Quantum computers exploit entanglement to perform certain calculations exponentially faster than classical computers. Quantum cryptography uses entanglement to create theoretically unbreakable codes. The security comes from the fact that any attempt to intercept the entangled particles would disturb them in a detectable way. Experiments have demonstrated entanglement across increasingly large distances. Satellites have established entanglement between particles separated by over 1,000 kilometers. The correlations persist regardless of distance, suggesting that space at the quantum level is not what it appears to be at larger scales. Some physicists interpret entanglement as evidence that space-time itself might emerge from deeper quantum connections, that the geometry of space might be built from patterns of entanglement in an underlying quantum structure. This idea, sometimes called entanglement as geometry or the ER equals EPR conjecture, suggests deep links between quantum mechanics, gravity, and the structure of space-time. At the heart of entanglement lies a profound mystery about the nature of reality. Before measurement, entangled particles exist in what's called a superposition, a state where they have all possible values simultaneously. Only upon measurement does this superposition collapse into a definite value. But the collapse of one particle's superposition instantly affects its entangled partner, no matter how distant. How information about the measurement propagates instantaneously across space without violating relativity remains one of the deepest puzzles in physics. Various interpretations of quantum mechanics offer different explanations. The Copenhagen interpretation suggests measurement causes a real collapse of the wave function. The many worlds interpretation proposes that all possible measurement outcomes occur, with the universe splitting into parallel branches. The pilot wave theory suggests particles have definite positions all along, guided by a quantum field. But none of these interpretations fully resolves the mystery of how entanglement works. In the quantum realm, particles maintain impossible correlations across the void, connected by invisible threads that transcend distance, operating by rules that challenge our deepest intuitions about the nature of reality. Most of the universe's energy is invisible and pushes galaxies apart. In the late 1990s, astronomers made a discovery that would revolutionize cosmology and win a Nobel Prize. By observing distant supernovae, they found that the expansion of the universe is not slowing down as expected, but accelerating. Something is pushing galaxies apart, overcoming the attractive force of gravity. This something comprises about 68% of all the energy in the universe, yet we have no idea what it is. We call it dark energy. For most of the 20th century, astronomers expected the universe's expansion to be slowing. The Big Bang sent everything flying outward, but gravity should pull everything back together, decelerating the expansion. The question was whether there was enough matter to eventually reverse the expansion and cause the universe to collapse in a big crunch, or whether it would expand forever, gradually slowing but never quite stopping. The truth proved stranger than either option. Distant type Ia supernova, exploding white dwarf stars that serve as standard candles for measuring cosmic distances, appeared fainter than expected. This meant they were farther away than calculations based on a decelerating universe predicted. The universe's expansion has been speeding up for the past several billion years. The simplest explanation for dark energy is the cosmological constant, a term Einstein added to his equations of general relativity, and later called his greatest blunder. The cosmological constant represents a uniform energy density of empty space itself. Every cubic meter of vacuum contains a tiny amount of energy, and this energy has a bizarre property. Unlike matter or radiation, whose gravity pulls things together, the cosmological constant has negative pressure, effectively pushing things apart. As the universe expands, the amount of matter and radiation in any given volume decreases as everything spreads out. But dark energy doesn't dilute. If it's truly a cosmological constant, then every cubic meter of space contains the same amount of dark energy, regardless of expansion. As the universe grows, the total amount of dark energy increases proportionally with volume. Eventually, dark energy comes to dominate over matter and radiation, and its repulsive effect accelerates the expansion. We appear to be living in the era when dark energy has recently become dominant, when the universe has transitioned from deceleration to acceleration. The cosmological constant interpretation faces a severe problem called the vacuum energy problem, or the cosmological constant problem. Quantum field theory predicts that empty space should be filled with quantum fluctuations, virtual particles constantly appearing and disappearing. These fluctuations should contribute to the vacuum energy density. When physicists calculate what this quantum vacuum energy should be, they get an answer about 10 to the 120 times larger than the observed dark energy density. This is the worst prediction in the history of physics, wrong by 120 orders of magnitude. Something is clearly missing from our understanding. Various solutions have been proposed. Perhaps the contributions from different quantum fields somehow cancel out almost perfectly, leaving only the tiny remainder we observe. Perhaps there's a symmetry we haven't discovered that forces the vacuum energy to be small. Perhaps dark energy isn't a cosmological constant at all, but something that varies in space and time, a dynamic field sometimes called quintessence. If dark energy is not constant but changing, it could eventually weaken, strengthen, or even reverse sign. The fate of the universe depends on dark energy's behavior. If dark energy is truly constant, the universe will expand forever at an accelerating rate. Distant galaxies will recede faster and faster, eventually moving away faster than light due to the expansion of space itself. In the far future, galaxies beyond our local group will disappear beyond the cosmic horizon, their light unable to reach us. The universe will grow dark and empty from our perspective, with only the local group of gravitationally bound galaxies remaining visible. If dark energy grows stronger over time, an outcome called phantom energy, the acceleration will increase until it tears apart galaxies, stars, planets, and eventually atoms themselves in a big rip. If dark energy weakens or reverses, the universe might eventually recollapse in a big crunch. Current observations suggest dark energy is consistent with a cosmological constant, but uncertainties remain large enough that other possibilities cannot be ruled out. Understanding dark energy is one of the central challenges of modern cosmology. It dominates the energy content of the universe and determines cosmic destiny. Yet we don't know what it is, why it has the value it does, or whether it will remain constant. Several major observational campaigns are underway to measure dark energy's properties more precisely. Large surveys map the distribution of galaxies across cosmic time, measure the expansion rate at different epochs, and observe how cosmic structure grows under dark energy's influence. Future space missions will measure dark energy's effect on cosmic expansion history with unprecedented precision. But observations alone may not suffice. We may need new theoretical insights, perhaps from a successful theory of quantum gravity, to truly understand what dark energy is and why the universe accelerates its expansion. For now, this mysterious energy remains one of the deepest puzzles in all of science, a reminder that even after centuries of progress, we remain profoundly ignorant about the fundamental nature of the cosmos. Empty space seethes with energy and virtual particles. Quantum mechanics tells us that even perfect vacuum, completely empty space devoid of all matter and radiation, is not truly empty. At the smallest scales, vacuum seethes with activity, a restless sea of quantum fluctuations where virtual particles constantly appear and disappear. These fluctuations are not just theoretical curiosities, but have measurable physical effects verified by precision experiments. The uncertainty principle, one of the cornerstones of quantum mechanics, states that you cannot simultaneously know both the position and momentum of a particle with perfect precision. A related form of the uncertainty principle applies to energy and time. For a sufficiently brief interval, energy conservation can be violated by an amount inversely related to the duration. This allows particle-antiparticle pairs to spontaneously appear from nothing, borrowing energy from the quantum vacuum as long as they annihilate quickly enough that the energy debt is repaid. These virtual particles exist for only the briefest instance, typically around 10 to the minus 23 seconds or less, but during their fleeting existence they have real effects. They alter the behavior of atoms, shift energy levels in predictable ways, and contribute to forces between particles. One of the most famous effects of vacuum fluctuations is the Casimir effect, first predicted in 1948 and experimentally confirmed in 1997. When two uncharged metal plates are placed very close together in vacuum, they experience an attractive force pushing them together. This happens because the quantum vacuum between the plates can only sustain fluctuations with wavelengths that fit exactly between the plates, while the vacuum outside can sustain all wavelengths. This difference in vacuum energy creates a pressure that pushes the plates together. The effect is extraordinarily small but measurable with sensitive instruments. Another effect is the Lamb shift, a tiny difference in the energy levels of hydrogen atoms discovered in 1947. According to the simple quantum theory of the atom, certain energy levels should be identical, but precise measurements show they differ slightly. The difference arises from interactions between the electron and the quantum vacuum fluctuations surrounding it. The virtual photons that appear and disappear near the electron slightly alter its effective mass and charge, shifting the energy levels in ways that can be calculated and measured with extraordinary precision. The agreement between theory and experiment for the Lamb shift and similar quantum electrodynamic effects is spectacular, confirming quantum field theory to more than 10 decimal places. Virtual particles also affect the strength of forces. The electromagnetic force between two electrons is mediated by the exchange of photons. But these photons can briefly fluctuate into electron-positron pairs, which affect how the force behaves. At short distances, this screening effect makes the electromagnetic force stronger than you'd expect from simple calculations. This running of coupling constants is now understood to be fundamental to particle physics, affecting all the forces of nature. The quantum vacuum has profound implications for cosmology as well. As mentioned earlier, quantum fluctuations should contribute to the vacuum energy density, creating an enormous cosmological constant. The fact that the observed dark energy density is so much smaller than quantum field theory predicts remains one of the deepest unsolved problems in physics. Some physicists have even suggested that the vacuum might not be stable. If our universe exists in a metastable vacuum state, like a ball sitting in a shallow valley with deeper valleys beyond, quantum fluctuations might eventually trigger a transition to a lower energy vacuum. Such a vacuum decay event would create a bubble expanding at the speed of light, fundamentally altering the laws of physics within the bubble and destroying everything in its path. There's no evidence we're in a metastable vacuum, and even if we are, the transition could be delayed for times vastly longer than the current age of the universe, but the possibility illustrates how quantum vacuum fluctuations shape not just particle physics, but the ultimate stability of space-time itself. The quantum vacuum is also thought to have played a crucial role in the very early universe. During cosmic inflation, quantum fluctuations in the inflaton field, the hypothetical field-driving inflation, were stretched to cosmic scales by the rapid expansion. These fluctuations seeded the tiny density variations we see in the cosmic microwave background, which eventually grew into galaxies and large-scale structure. In this sense, every galaxy, every star, and everything in the universe arose from quantum fluctuations in the vacuum during the first fraction of a second after the Big Bang. In the apparent emptiness of space lies a hidden vitality, a quantum foam of particles flickering in and out of existence, shaping atoms, forces, and possibly the cosmos itself. the universe might end by tearing apart every atom. The discovery that dark energy is accelerating the universe's expansion raises profound questions about cosmic destiny. If dark energy remains constant, the universe will expand forever, growing ever colder and emptier. But if dark energy strengthens over time, the fate could be far more dramatic and violent. Physicists call this possibility the Big Rip, a scenario in which the accelerating expansion becomes so extreme that it tears apart galaxies, stars, planets, atoms, and eventually the fabric of space-time itself. In the Big Rip scenario, dark energy is modeled as phantom energy, a hypothetical form of dark energy whose density increases as the universe expands rather than remaining constant. This violates the dominant energy condition, a principle from general relativity, but is not strictly forbidden by known physics. As phantom energy grows stronger, the expansion of space accelerates more and more rapidly. Distant galaxies already recede faster than light due to cosmic expansion. In a Big Rip scenario, this would continue until even nearby objects begin to accelerate away. Calculations suggest a sequence of cosmic dissolution. First, billions of years in the future, the accelerating expansion begins to affect galaxy clusters. Galaxies on the outskirts of clusters are pulled away faster than gravity can hold them. The clusters dissolve, with galaxies drifting into isolation. Then, individual galaxies begin to feel the effect. Stars on the outer edges of galaxies are torn away as space expands faster than their orbital velocity can compensate. Galaxies come apart, scattering their stars into the expanding void. As the expansion continues to accelerate, even solar systems cannot remain bound. About 60 million years before the final rip, the Earth would be torn from its orbit around the Sun. The planet would drift alone through space, rapidly cooling as it recedes from its star. Months before the end, planetary systems themselves come apart. Any remaining planets are torn into pieces as the expansion overcomes the gravitational forces holding them together. Minutes before the rip, molecules are torn apart. The expansion of space becomes so rapid that even chemical bonds cannot resist. Complex structures dissolve into clouds of individual atoms. In the final fraction of a second, atoms themselves are destroyed. Electrons are torn from their nuclei. Then atomic nuclei are ripped apart. Even subatomic particles may be shredded as space-time itself becomes unstable. The universe ends not in cold darkness, but in a final paroxysm of destruction. Is this our fate? Current observations suggest it's unlikely, but not impossible. Measurements of dark energy indicate it behaves very much like a cosmological constant, neither strengthening nor weakening as the universe expands. But the uncertainties are still large enough that phantom energy cannot be completely ruled out. Future observations, particularly measurements of how dark energy evolves over cosmic time, will constrain the possibilities more tightly. If dark energy is indeed constant, the universe faces a different but equally profound fate, sometimes called the Big Freeze, or heat death. In this scenario, the universe expands forever at an accelerating rate. Stars exhaust their nuclear fuel and die. Galaxies grow dark. Even black holes eventually evaporate through Hawking radiation. After unimaginably long times, perhaps 10 to the 100 years or more, the universe contains only a thin gruel of photons, neutrinos, and other particles, growing ever more dilute as space expands. The temperature approaches absolute zero. Entropy approaches its maximum. The universe reaches a state of equilibrium where nothing interesting can ever happen again. there are other possibilities. If dark energy weakens or reverses sign, the expansion could slow and even reverse, leading to a big crunch where the universe collapses back on itself. Some cyclic models propose that the universe oscillates between big bangs and big crunches, eternally creating and destroying itself. The ultimate fate of the universe remains genuinely unknown, dependent on the nature of dark energy which we do not yet understand. But whether the cosmos ends in ice, fire, or some other fate, the timescales involved are so vast that they defy comprehension, trillions of years or more before any final fate arrives. For now, and for countless generations to come, the universe remains young, vibrant, and full of structure and complexity. The stars still shine, galaxies still spiral, and life still finds its footholds in the vast cosmic ocean. Space-time ripples carry energy across the universe. In November 2015, humanity detected something Einstein predicted a century earlier, but thought would never be observed. Gravitational waves, ripples in space-time itself, had crossed the universe and gently shook the Earth. The detection opened an entirely new window on the cosmos and confirmed one of the most profound predictions of general relativity. Gravitational waves are fundamentally different from electromagnetic waves. Light is made of photons, particles of electromagnetic radiation that propagate through space-time. Gravitational waves are ripples in space-time itself, traveling perturbations in the geometry of space and time. When a gravitational wave passes through you, space itself alternately stretches and squeezes in perpendicular directions. The effect is tiny. Even from the most violent cosmic events, gravitational waves stretch space by less than 1 part in 10 to the 21st. Detecting such minuscule distortions requires extraordinary experimental ingenuity. The LIGO observatories accomplish this using laser interferometry. Each LIGO detector consists of 2 arms, each 4 kilometers long, arranged in an L shape. Laser beams travel down both arms, bounce off mirrors at the ends, and return to recombine at the corner. Normally, the beams are perfectly out of phase and cancel each other out. But when a gravitational wave passes through, one arm becomes slightly longer while the other becomes slightly shorter, changing the interference pattern in a measurable way. The challenges are immense. LIGO must distinguish the signal from countless sources of noise. Seismic vibrations from earthquakes, passing trucks, even ocean waves breaking on distant shores create vibrations that dwarf the gravitational wave signal. Thermal noise causes the mirrors to jiggle randomly. Even quantum fluctuations in the laser light create uncertainty in the measurements. Through sophisticated isolation systems, advanced optics, and careful data analysis, LIGO filters out the noise and reveals the gravitational wave signals. Since the first detection in September 2015, LIGO and its partner Virgo have detected dozens of gravitational wave events. Most are from merging black holes, but others come from colliding neutron stars and possibly from other exotic sources. Each detection provides unique information. From the waveform, astronomers can determine the masses and spins of the merging objects, the distance to the merger, and even test general relativity under the most extreme conditions. The discovery of gravitational waves from a neutron star merger in August 2017 marked a milestone. For the first time, a cosmic event was observed in both gravitational waves and electromagnetic radiation, creating the new field of multi-messenger astronomy. The gravitational waves arrived first, alerting astronomers to the event. Within seconds, a gamma ray burst was detected. Within hours, dozens of telescopes around the world and in space were observing the aftermath, detecting visible light, X-rays, and radio waves from the kilonova explosion created by the merger. This single event confirmed that neutron star mergers are the source of short gamma-ray bursts, demonstrated that heavy elements like gold and platinum are forged in these cosmic collisions, measured the expansion rate of the universe through an independent method, and tested whether gravitational waves and light travel at the same speed. They do, to within 1 part in 10 to the 15th. Gravitational wave astronomy is still in its infancy. Future detectors will be far more sensitive. LIGO is being upgraded to Advanced LIGO Plus. The planned Einstein Telescope and Cosmic Explorer will be next-generation ground-based detectors capable of seeing black hole mergers across the entire observable universe. The space-based LISA mission, planned for the 2030s, will detect low-frequency gravitational waves from supermassive black hole mergers, extreme mass ratio inspirals where stellar mass objects spiral into supermassive black holes, and possibly from exotic sources like cosmic strings or phase transitions in the early universe. Gravitational waves might even allow us to observe the Big Bang itself. Electromagnetic radiation from earlier than 380,000 years after the Big Bang cannot reach us because the universe was opaque to light before then. But gravitational waves can travel through anything. If we could detect primordial gravitational waves from the era of cosmic inflation, just a tiny fraction of a second after the Big Bang, we would have a direct window on the moment of creation itself. This remains a goal for future experiments. In the subtle vibrations of space-time, in ripples so faint they can barely be measured even with our most sophisticated instruments, we find a new way of listening to the universe, a way to hear the collisions of black holes, the mergers of neutron stars, and perhaps one day the echoes of the Big Bang itself. The universe's age is etched in ancient light. When we look at the night sky, we look into the past. Light from the sun takes 8 minutes to reach us, so we see the sun as it was 8 minutes ago. Light from the nearest star takes over 4 years to arrive, showing us that star as it was 4 years in the past. Light from distant galaxies has traveled for billions of years, revealing those galaxies as they were in the ancient cosmos. The most distant light we can detect comes from nearly the beginning of time itself, carrying information about the infant universe. This most ancient light is the cosmic microwave background, radiation that fills all of space uniformly, coming from every direction with almost exactly the same properties. It has a temperature of 2.7 Kelvin, only a few degrees above absolute zero, and peaks in the microwave part of the spectrum. This radiation is the cooled remnant of the hot plasma that filled the universe in its infancy. In the first few 100,000 years after the Big Bang, the universe was filled with hot plasma, a soup of electrons and atomic nuclei so hot that they couldn't combine into neutral atoms. Any photon traveling through this plasma would immediately collide with an electron and scatter in a new direction. The universe was opaque, foggy, like being inside a cloud. But as the universe expanded, it cooled. About 380,000 years after the Big Bang, the temperature dropped enough for electrons to combine with nuclei to form neutral hydrogen and helium atoms. This moment is called recombination, though it's a misnomer since the atoms were combining for the first time, not recombining. Once recombination occurred, photons could travel freely through space without scattering. The universe became transparent. The cosmic microwave background is the light from this moment, the first light that could travel freely through space. We call it the surface of last scattering. Every photon in the cosmic microwave background has been traveling through space for 13.8 billion years, from the era when the universe was 1,000th of its current size. As the universe expanded, these photons were stretched to longer wavelengths, redshifted from visible and infrared light to microwaves. The cosmic microwave background is remarkably uniform. In every direction, its temperature is almost exactly 2.725 Kelvin, but not perfectly uniform. Tiny variations exist, deviations of only a few hundred millionths of a degree, but these tiny ripples carry enormous information. They show us the density variations that existed in the infant universe, the seeds from which all cosmic structure grew. The patterns in these temperature fluctuations tell us about the composition of the universe, the geometry of space, the rate of cosmic expansion, and countless other cosmological parameters. By analyzing the cosmic microwave background in exquisite detail, astronomers have determined the age of the universe, 13.8 billion years, to within 1% accuracy. They've measured the composition, 4.9% ordinary atoms, 26.8% dark matter, and 68.3% dark energy. They've determined that the universe is spatially flat on large scales, meaning its geometry is Euclidean rather than curved. They've confirmed the predictions of cosmic inflation, a period of exponential expansion in the first fraction of a second after the Big Bang. The cosmic microwave background even reveals information about events that happened during the first moments of existence, when the universe was less than a second old. Satellites like COBE, WMAP, and Planck have mapped the cosmic microwave background with increasing precision, creating baby pictures of the universe that reveal its structure at age 380,000 years. Future experiments aim to detect even fainter signals, including the imprint of primordial gravitational waves on the polarization of the cosmic microwave background. Such a detection would provide direct evidence of cosmic inflation and probe physics at energy scales far beyond anything achievable in particle accelerators. In the faint microwave glow that bathes the universe, we find the light of creation, cooled and stretched by expansion but carrying within it the encoded history of cosmic dawn, a message from the beginning of time itself. And now we arrive at the deepest questions of all, the mysteries that touch upon life itself and our place in this vast cosmos. Here, in the quiet contemplation of existence, we explore the greatest enigma, the question that has driven humanity to build telescopes and spacecraft and search the skies with longing. Are we alone? And what does it mean that in 13.8 billion years of cosmic history, in a universe containing hundreds of billions of galaxies, we have not yet found a single sign of others like us? Let us drift through these final mysteries with wonder and humility, exploring the boundaries between the known and the unknown. The universe seems empty of other technological civilizations. In 1950, physicist Enrico Fermi asked a question that has puzzled scientists ever since. If intelligent life is common in the universe, where is everybody? The question, now known as the Fermi paradox, highlights an apparent contradiction between the high probability that extraterrestrial civilizations should exist and the complete absence of evidence for them. Let us consider the numbers. Our galaxy contains between 100 billion and 400 billion stars. Recent discoveries suggest most stars have planets. meaning there are likely hundreds of billions of planets in the Milky Way alone. Many of these planets orbit in the habitable zone, the region around a star where temperatures allow liquid water to exist on a planet's surface. Conservative estimates suggest there could be billions of potentially habitable planets in our galaxy. The universe contains roughly 2 trillion galaxies in the observable universe. If even a tiny fraction of planets develop life, and if even a tiny fraction of those develop intelligent life, and if even a tiny fraction of those develop a technology, there should be millions or billions of technological civilizations in the observable universe. Some of these civilizations might be far older than humanity. Our Sun is a relatively young star, only 4.6 billion years old. Many stars formed billions of years earlier, potentially giving life on planets around those stars a huge head start. A civilization even a few million years more advanced than humanity might have capabilities we can barely imagine. They might have colonized their entire galaxy, built vast structures visible across interstellar distances, or developed communication technologies that flood the cosmos with signals. Yet we see none of this. The sky is dark and silent. Despite decades of searching for radio signals from extraterrestrial civilizations, despite increasingly sophisticated observations of nearby stars and galaxies, despite careful analysis of astronomical data for signs of megastructures or other technological artifacts, we have found nothing. No signals, no structures, no visitors. Nothing that unambiguously indicates the presence of another technological civilization anywhere in the observable universe. This silence is the Fermi paradox. Many potential solutions have been proposed, each with different implications for humanity's future and our place in the cosmos. Perhaps intelligent technological life is extraordinarily rare. Maybe one or more steps in the evolution from non-living chemistry to technological civilization are so improbable that it happens only a handful of times per galaxy or less. The origin of life itself might be the rare step. Despite decades of research, we still don't fully understand how non-living chemistry transitions to biology. Laboratory experiments have shown that some building blocks of life, amino acids and nucleotides, can form through natural chemical processes. But creating a self-replicating system capable of evolution remains beyond our current abilities. If life requires a long series of unlikely chemical accidents to begin, it might be exceedingly rare. Or perhaps life itself is common, but intelligence is rare. On Earth, life existed for 3.5 billion years before anything we'd recognize as intelligent emerged. For most of Earth's history, life consisted of single-celled microbes. Complex, multicellular life didn't evolve until about 600 million years ago. Intelligence requiring large brains only evolved in the last few million years, and technological civilization emerged only in the last few thousand years. Perhaps most planets with life never progress beyond microbes, or, if they do, never evolve intelligence and technology. Another possibility is that civilizations are common but short-lived. Perhaps technological civilizations inevitably destroy themselves through war, environmental catastrophe, resource depletion, or other disasters shortly after developing advanced technology. If the typical technological civilization lasts only a few hundred or thousand years before collapsing, then at any given moment, very few would exist. The galaxy might have hosted millions of civilizations over its history, but they rose and fell in temporal isolation, never overlapping enough to make contact. This possibility, sometimes called the Great Filter, suggests that there is some extremely difficult step in the evolution from simple matter to enduring spacefaring civilization, a filter that almost nothing passes through. The terrifying question is whether the filter is behind us or ahead of us. If it's behind us, if the rare step is the origin of life or the evolution of intelligence, then we are fortunate survivors and may have a long future ahead. If the filter is ahead of us, if civilizations routinely self-destruct shortly after achieving technology, then humanity may be approaching our own extinction. Some solutions to the Fermi paradox suggest that civilizations exist but are not detectable. Perhaps advanced civilizations deliberately hide themselves, wary of attracting attention from potential threats. Perhaps they communicate using methods we haven't discovered or don't recognize. Perhaps they exist in forms so different from us that we wouldn't recognize them as life. Perhaps they're not interested in communication or expansion, content to develop inwardly rather than spreading across the galaxy. Another class of solution suggests that the assumptions underlying the paradox are wrong. Perhaps interstellar travel and communication are far more difficult or expensive than we imagine, making it impractical for civilizations to expand beyond their home systems or to conduct extensive searches for others. Perhaps the speed of light truly is an insurmountable barrier, making the galaxy effectively too large for civilizations to ever make contact even if many exist. Perhaps we simply haven't searched long enough or carefully enough, and evidence exists that we haven't yet found. The Fermi paradox remains unresolved, a profound mystery that touches on questions of biology, evolution, technology, sociology, and the ultimate fate of intelligent species. Every additional year, we search the skies and find silence makes the paradox deeper. In that silence, we might find warning or uniqueness, or simply the vastness of space and time keeping civilizations forever apart. Life thrives in Earth's harshest environments, expanding the possibilities. For most of history, scientists assumed life required moderate conditions, comfortable temperatures, abundant water, and sunlight for photosynthesis. But discoveries over the past few decades have shattered these assumptions. Life exists in environments that seem utterly hostile, places once thought to be completely sterile. These extremophils, organisms that thrive in extreme conditions, have revolutionized our understanding of life's possibilities and expanded the range of environments where we might search for life elsewhere. In the crushing depths of the ocean, miles below the surface where pressure exceeds 1,000 atmospheres and sunlight never penetrates, life flourishes around hydrothermal vents. These underwater hot springs spew water heated to temperatures exceeding 700 degrees Fahrenheit, though it doesn't boil due to the immense pressure. The water is laden with toxic chemicals like hydrogen sulfide and heavy metals. Yet dense communities of life surround these vents, including tube worms, clams, crabs, and fish, all supported by bacteria that extract energy from the chemicals in the vent fluids rather than from sunlight. This process, called chemosynthesis, demonstrates that life doesn't require photosynthesis or any connection to the sun's energy. In the dry valleys of Antarctica, among the coldest and driest places on Earth, where some regions haven't seen rainfall for millions of years and temperatures remain below freezing most of the year, microorganisms survive in rocks, in the soil, and beneath the ice. Some organisms remain frozen for months at a time, their metabolism reduced to nearly nothing. Yet they revive when brief moments of warmth provide liquid water. In the scalding waters of hot springs in places like Yellowstone National Park, where temperatures reach near or even above the boiling point of water. Thermophilic bacteria and archaea thrive. Some species have optimal growth temperatures above 120 degrees Celsius, well above water's boiling point at sea level. These organisms have proteins and enzymes specially adapted to remain stable and functional at temperatures that would destroy the molecular machinery of ordinary life. In extremely acidic environments, with pH values near zero comparable to battery acid, acidophilic organisms make their living. In extremely alkaline environments with pH values above 11, alkaliphiles thrive. In salt lakes and salt mines where salt concentration exceeds 30%, far saltier than ocean water, halophilic archaea grow. These salt lovers require high salt concentrations and would die in normal seawater or fresh water. In rock deep beneath Earth's surface, miles underground where no sunlight penetrates and the overlying rock exerts tremendous pressure. Endolithic microorganisms live within the rock itself, extracting energy from chemical reactions between rock and water. Some of these deep subsurface organisms live in complete isolation from the surface world, sustained by geology rather than biology. Radiation-resistant organisms can survive radiation doses thousands of times higher than would be lethal to humans. The bacterium Deinococcus radiodurans can survive radiation that shatters its DNA into hundreds of fragments, then accurately reassemble its genome and continue growing. This resistance likely evolved as an adaptation to extreme desiccation rather than radiation, but it demonstrates that life can develop extraordinary repair mechanisms. Perhaps most remarkably, tardigrades or water bears, microscopic animals visible under a microscope, can survive conditions that would seem impossible. They can be frozen to near absolute zero, heated to over 300 degrees Fahrenheit, survive decades without water by desiccating into a dormant state, endure radiation levels far beyond what would kill any other animal, and even survive exposure to the vacuum of space. Experiments have sent tardigrades into orbit, where they were exposed to space vacuum and solar radiation. Most survived and resumed normal activity upon return to Earth. These extremophiles have profound implications for astrobiology. If life can thrive in Earth's most hostile environments, then potentially habitable environments might exist in places we'd previously dismissed as too extreme. The subsurface oceans of Europa, Enceladus, and other icy moons suddenly seem like promising habitats. The cold, dry surface of Mars, while hostile, might harbor microbial life in protected niches. Even the acidic clouds of Venus have been considered as potential habitats, though this remains highly speculative. The discovery of extremophiles also informs how we search for life. We cannot assume that life elsewhere will resemble familiar Earth organisms or require Earth-like conditions. Life might be far more adaptable and creative than we imagined, capable of exploiting energy sources and environments we haven't considered. When we design missions to search for life on other worlds, we must think broadly about what signatures life might produce and what environments it might inhabit. In the scalding vents and frozen wastes where Earth's extremophiles make their homes, we find expanded horizons for life's possibilities and hope that the universe might be more fertile than we dared imagine. The ingredients of life might be common, but life itself remains mysterious. Whenever we find liquid water, organic molecules, and an energy source on Earth, we find life. These appear to be the basic requirements, the minimum ingredients from which biology can emerge. And, remarkably, these ingredients seem to be common throughout the universe. Water is abundant in the cosmos. It forms naturally when hydrogen, the most common element, combines with oxygen, the third most common element. We have detected water in interstellar clouds, on planets and moons throughout our solar system, in comets and asteroids, even in the atmospheres of planets orbiting distant stars. Water's unique properties, its ability to dissolve many substances, its expansion when freezing, its high heat capacity, make it an ideal medium for the chemistry of life. Organic molecules, compounds containing carbon, are also widespread. Carbon's ability to form stable bonds with many other elements, creating complex molecules with diverse properties, makes it the foundation of life as we know it. Observations of interstellar clouds have revealed over 200 different organic molecules in space, including amino acids, the building blocks of proteins, and nucleobases, components of DNA and RNA. Meteorites that fall to Earth often contain organic compounds, including amino acids and more complex molecules. The Murchison meteorite, which fell in Australia in 1969, contained over 90 different amino acids, only 19 of which are found in Earth life, proving these molecules form naturally through abiotic chemistry. Energy sources are also common. Sunlight bathes the surfaces of planets. Radioactive decay in planetary interiors provides heat. Tidal forces from gravitational interactions generate warmth. Chemical energy exists wherever different substances can react. Throughout the cosmos, sources of energy that life might exploit are available. Yet, despite the apparent abundance of life's ingredients, we don't know how common life actually is. We have only one example, Earth, where life definitely exists. We don't know if life on Earth represents a common outcome when the right ingredients come together, or an extraordinarily improbable accident that may never have occurred elsewhere. The origin of life, the transition from non-living chemistry to self-replicating biological systems, remains one of the deepest unsolved problems in science. We know it happened at least once, on Earth, but we don't know how. Various hypotheses have been proposed for how life began. The primordial soup hypothesis suggests that in Earth's early oceans, organic molecules accumulated and underwent increasingly complex chemical reactions until self-replicating molecules emerged. The RNA world hypothesis proposes that early life was based on RNA rather than DNA, with RNA serving both as genetic material and as catalytic molecules before DNA and proteins evolved. The iron-sulfur world hypothesis suggests life began at hydrothermal vents, where minerals catalyzed the formation of organic molecules. The panspermia hypothesis proposes that life didn't originate on Earth at all, but arrived from space, perhaps carried by comets or asteroids, though this just moves the question of origins to another location. Laboratory experiments have made progress in understanding pieces of the puzzle. The famous Miller-Urey experiment in 1953 showed that amino acids could form spontaneously when a mixture of simple gases thought to resemble Earth's early atmosphere was subjected to electrical sparks simulating lightning. Subsequent experiments have shown that nucleotides, lipids, and other biological building blocks can form through natural chemistry. Researchers have created self-replicating RNA molecules in the laboratory, demonstrating that RNA can serve both as information storage and as catalyst. But no experiment has yet created anything approaching a living cell from scratch. The gap between complex organic chemistry and even the simplest bacterium remains vast. The simplest known living cells contain hundreds of genes, encoding hundreds of different proteins working together in coordinated metabolic networks. How such complexity could arise from chemistry is unclear. Perhaps life requires some special conditions we haven't identified, some specific sequence of chemical steps that's difficult to achieve. Perhaps it requires luck, random molecular arrangements that are possible but improbable, making life rare even when the ingredients are present. Or perhaps the transition from chemistry to biology is more inevitable than we think, and life arises readily whenever conditions allow. We simply don't know. The search for life beyond Earth is partly an attempt to answer this question. If we find life elsewhere in our solar system, on Mars or Europa or Enceladus, and if that life has a separate origin from Earth life rather than being related through panspermia, it would suggest life arises readily when conditions permit. Finding even one additional origin of life would transform our understanding, suggesting the universe might be teeming with biology. Conversely, if we explore the solar system thoroughly and find Earth is the only place where life emerged, it would suggest life is rare, that the origin requires something special that's uncommon even when the basic ingredients are present. Some scientists have proposed biosignature gases that might reveal the presence of life on distant exoplanets. On Earth, oxygen in the atmosphere is maintained by photosynthesis. Without life continuously producing oxygen, it would react with rocks and organic matter and disappear from the atmosphere within a few million years. Detecting oxygen, along with other gases like methane that are chemically incompatible, both existing simultaneously because life produces both, could be a signature of biology. Future space telescopes may be able to detect such biosignatures in the atmospheres of Earth-like planets orbiting nearby stars. In the abundance of water, organics, and energy throughout the cosmos, we find reason for hope. But in our profound ignorance about how life begins, we find humility and mystery. Phosphorus is essential for life, but rare in the universe. Every living thing on Earth, from bacteria to blue whales, from algae to humans, requires phosphorus. It's an essential element for life, a component of DNA and RNA, where it forms the backbone of the genetic molecule, a key ingredient in ATP which stores and transports energy within cells, and a structural component of cell membranes. Without phosphorus, life as we know it cannot exist. Yet phosphorus presents a cosmic problem. It's rare in the universe compared to other elements essential for life like carbon, nitrogen, and oxygen. This phosphorus scarcity might limit where life can emerge, and could partly explain why we haven't detected life elsewhere. Phosphorus forms through nucleosynthesis, the process of creating heavier elements from lighter ones through nuclear fusion. But, unlike carbon, nitrogen, and oxygen, which form in all massive stars, phosphorus requires specific conditions. It's created primarily in supernovae, the explosive deaths of massive stars, and even then, only in modest quantities. When astronomers measure the abundance of elements in the universe, they find phosphorus is about 10 to 20 times less abundant than nitrogen, and hundreds of times less abundant than carbon. But the problem goes deeper than simple abundance. Phosphorus doesn't remain in forms that life can use. In rocky planets like Earth, most phosphorus is locked up in minerals like apatite, where it's chemically bound to calcium and other elements. Making phosphorus biologically available requires processes that liberate it from these minerals. On Earth, weathering of rocks gradually releases phosphate into rivers and oceans where organisms can use it. Volcanic activity brings phosphorus-rich materials to the surface. Lightning strikes can even convert some forms of phosphorus into more accessible varieties, Yet, even on Earth, phosphorus is often a limiting nutrient, the element whose scarcity limits biological productivity in many ecosystems. The phosphorus cycle operates slowly, and in some environments, lack of phosphorus constrains how much life can exist. For other worlds, especially those without active geology to recycle nutrients or without liquid water to distribute them, obtaining sufficient bioavailable phosphorus could be extremely difficult. The phosphorus problem becomes more severe when considering where phosphorus comes from. Massive stars that produce phosphorus in supernova are relatively rare, and they live only a few million years before exploding. A planetary system needs to form in a region where supernova explosions have already occurred, enriching the local interstellar medium with heavy elements including phosphorus. Very old stars that formed early in galactic history, before many supernovae had occurred, would have planets extremely depleted in phosphorus and other heavy elements. This suggests life might be limited to planets forming relatively recently in cosmic history, after enough stellar generations have enriched the galaxy with heavy elements. Some regions of the galaxy, particularly the dense central regions, might have experienced more supernovae and thus have more phosphorus available. But these regions also experience higher rates of catastrophic events like nearby supernovae and gamma-ray bursts that could sterilize planets. There might be a galactic habitable zone, regions of the galaxy where phosphorus and other heavy elements are abundant enough for life, but supernova rates are low enough that planets aren't constantly irradiated. Recent research has suggested that rocky planets similar to Earth might be able to form only in the outer regions of galaxies where conditions are similar to our solar system's neighborhood. Planets forming in the galactic center or too far in the outer regions might lack sufficient heavy elements or have other problems that make them unsuitable for life. Alternative biochemistries using different elements have been proposed, but phosphorus is difficult to replace. Its chemical properties, particularly its ability to form stable bonds in both water-soluble and structural roles, make it uniquely suited for biology. Silicon has been suggested as an alternative to carbon, and ammonia as an alternative to water, but no convincing substitute for phosphorus has been identified. This suggests that life elsewhere in the universe, if it exists, might face the same phosphorus limitation Earth life does, requiring access to this relatively rare element. Missions searching for life on other worlds consider phosphorus when evaluating habitability. Mars has phosphorus in its rocks, but whether it's accessible in forms life could use is unclear. Europa's ocean might contain phosphorus leached from the rocky seafloor, but concentrations are unknown. Exoplanets being evaluated for habitability must have not only liquid water and organic compounds, but also sufficient quantities of essential elements like phosphorus. In this single element, essential yet scarce, we find another factor shaping where life can exist in the cosmos, another filter determining which of the countless worlds in the universe might host biology. We still don't know how life began on Earth. Despite decades of research, scientists have not succeeded in creating life from non-living matter in the laboratory. Nor have we definitively determined how life originated on Earth 4 billion years ago. This gap in knowledge represents one of the most fundamental unsolved questions in science. What we do know provides some constraints. Life on Earth uses DNA to store genetic information, RNA to translate that information into instructions, and proteins to carry out most cellular functions. All life uses the same genetic code with only minor variations, suggesting all Earth life descends from a single common ancestor. This last universal common ancestor, sometimes called Luca, lived perhaps 3.5 to 4 billion years ago. But Luca itself was already a sophisticated organism with DNA, RNA, proteins, metabolism, and cellular structures. The origin of life must have occurred earlier, perhaps in Earth's first few hundred million years. The young Earth was a harsh place. The planet was still being bombarded by asteroids and comets during a period called the Late Heavy Bombardment. The atmosphere lacked oxygen and may have been rich in methane, ammonia, carbon dioxide, and nitrogen. Volcanic activity was intense. Lightning was frequent. Ultraviolet radiation from the sun bombarded the surface since there was no ozone layer to block it. Yet somehow, in this hostile environment, life emerged. The RNA world hypothesis is currently the leading scientific explanation for life's origin. This idea proposes that early life was based on RNA rather than DNA. RNA can store genetic information like DNA, but it can also catalyze chemical reactions like proteins. Modern cells contain catalytic RNA molecules called ribozymes that perform essential functions, suggesting RNA's catalytic abilities are not just theoretical, but are actually used in biology. In the RNA world scenario, self-replicating RNA molecules arose through natural chemistry. These RNA molecules could make copies of themselves, though imperfectly, introducing variations. Some variants replicated more efficiently than others, creating a primitive form of natural selection. Over time, RNA molecules evolved greater complexity, eventually catalyzing the synthesis of proteins, which proved even more effective as catalysts. DNA, which is more chemically stable than RNA, later evolved as a better information storage medium. This transition from RNA to DNA and proteins gave rise to the cells we see today. But the RNA world hypothesis faces challenges. How did the first self-replicating RNA arise? RNA is a complex molecule whose synthesis requires several steps. Creating RNA under plausible early Earth conditions has proven difficult in laboratory experiments, though some progress has been made. Researchers have shown that nucleotides, the building blocks of RNA, can form through chemistry alone. Chains of nucleotides can spontaneously form under certain conditions. But creating an RNA molecule capable of catalyzing its own replication remains elusive. Alternative hypotheses have been proposed. The metabolism first hypothesis suggests that self-sustaining networks of chemical reactions arose before genetic molecules, with simple metabolic cycles emerging first and genetics evolving later as a way to make the metabolism more reliable. The lipid world hypothesis proposes that simple cellular compartments formed first, creating microscopic bubbles that concentrated organic molecules and provided protected environments where more complex chemistry could occur. The hydrothermal vent hypothesis suggests life began in the warm, mineral-rich waters around underwater volcanic vents, with minerals providing catalytic surfaces that facilitated organic chemistry. Some researchers investigate whether life could have begun with genetic systems other than RNA. Perhaps simpler molecules preceded RNA, serving as primitive genetic material before RNA evolved. Or perhaps life began multiple times with different chemical foundations, and RNA-based life was simply the variant that succeeded and spread. The definition of life itself is debated. When does a system of chemical reactions cross the threshold from complex chemistry to actual life? Properties often associated with life include self-replication, metabolism, evolution through natural selection, and compartmentalization within boundaries like cell membranes. But exactly which properties are essential and how they first arose remain uncertain. Understanding the origin of life has implications beyond Earth. If we determine that life arises easily through natural chemistry given the right conditions, it suggests life might be common throughout the universe. If instead life requires extraordinarily specific circumstances or long series of improbable events, it suggests life might be exceedingly rare, making Earth perhaps the only living world in our galaxy or even in the observable universe. Future research may provide answers. Laboratory experiments continue to explore how life's building blocks can form and assemble into more complex structures. Simulations model early Earth conditions and test whether proposed origin scenarios are chemically plausible. Studies of extremophiles reveal how simple life can be while still functioning. And searches for life on Mars and other worlds might reveal whether life arose independently elsewhere, potentially showing us examples of different origin pathways. For now, the spark that ignited life remains mysterious, hidden in deep time, leaving us to wonder at the remarkable fact of our own existence, and to search for the chemical pathways that transformed sterile rock and water into the living world we inhabit. Physical constants appear impossibly fine-tuned for existence. The universe operates according to physical laws expressed through mathematical equations containing certain fundamental constants. These constants, values like the speed of light, the gravitational constant, the strength of electromagnetic force, and the masses of fundamental particles, define how the universe behaves. But here's something remarkable and deeply mysterious. If these constants were even slightly different from their actual values, the universe would be completely unable to support life or even to form complex structures like stars and atoms. This observation is called the fine-tuning problem, and it represents one of the deepest puzzles in physics. Consider the cosmological constant, the energy density of empty space that we call dark energy. Its measured value is extraordinarily small, about 10 to the minus 122 in natural units. Yet, quantum field theory predicts it should be about 10 to the 118 times larger, a discrepancy of 120 orders of magnitude. If the cosmological constant were much larger than observed, say 1,000 times bigger, the universe would have expanded so rapidly that matter could never have clumped together to form galaxies and stars. If it were negative, the universe would have recollapsed shortly after the Big Bang. Only in a narrow range near its observed value can a universe exist long enough and expand slowly enough for structure to form. The ratio of electromagnetic force to gravitational force is another example. Electromagnetism is about 10 to the 36 times stronger than gravity. This enormous difference is crucial. If gravity were relatively stronger, stars would be much smaller and burn out much faster, leaving insufficient time for life to evolve. If electromagnetism were relatively weaker, atoms couldn't form stable complex molecules. The masses of fundamental particles also appear fine-tuned. The mass difference between the up quark and down quark, which make up protons and neutrons, is critical. If this difference were slightly larger or smaller, the chemistry of atoms would change in ways that would prevent complex molecules and likely prevent any chemistry capable of supporting life. The strength of the strong nuclear force, which binds protons and neutrons in atomic nuclei, is similarly critical. If it were a few percent stronger, all hydrogen would have fused into helium shortly after the Big Bang, leaving no hydrogen to form water or organic molecules. If it were a few percent weaker, atomic nuclei beyond hydrogen could not form, meaning no heavy elements and no chemistry. Even the existence of carbon, essential for life as we know it, depends on an apparent coincidence. Carbon forms inside stars through a series of nuclear reactions. For carbon to be produced in sufficient quantities, an excited energy level in the carbon-12 nucleus must exist at just the right energy to allow a resonant nuclear reaction. This energy level, predicted by astronomer Fred Hoyle before it was measured, exists almost exactly where it needs to be for carbon synthesis. If it were slightly different, stars would produce almost no carbon. Some physicists estimate that if you randomly selected values for the fundamental constants, the probability of getting a universe capable of supporting any form of complexity, let alone life, would be astronomically small, perhaps less than 1 chance in 10 to the 60th, or even smaller. This fine-tuning seems to demand explanation. Why does the universe have these specific values rather than others? 3 main classes of explanation have been proposed. The first is necessity. Perhaps the constants cannot have other values. Maybe there's some deeper law or principle we haven't discovered that requires them to be what they are. Perhaps all apparently independent constants are actually related through some unified theory, and calculating any one of them would reveal they must have their observed values. This would dissolve the fine-tuning problem by showing the values aren't arbitrary, but necessary. The second explanation is chance. Perhaps we simply got lucky, and our universe happens to have constants compatible with complexity and life, even though most possible universes wouldn't. This seems deeply unsatisfying to many physicists, invoking incredible luck without explanation, but it cannot be definitively ruled out. The third explanation is the multiverse. If there exist many universes, perhaps infinitely many, with different values of the fundamental constants in each, then the fine-tuning problem dissolves. Most universes would be sterile, incapable of supporting life or complexity. But in the tiny fraction of universes where constants happen to allow complexity, observers can exist to wonder about the constants. We find ourselves in a life-permitting universe, not because such universes are common, but because we couldn't exist in any other kind. This is an application of the anthropic principle, the observation that any properties we observe the universe to have must be compatible with our existence as observers. The multiverse explanation is controversial because other universes, if they exist, would appear to be unobservable by definition, making the hypothesis difficult or impossible to test. Yet some versions of multiverse theory, particularly those emerging from eternal inflation models in cosmology, make predictions that might be testable. The fine-tuning problem touches on profound questions about the nature of reality, the relationship between mathematics and physics, and our role as observers. Are the constants truly fine-tuned, suggesting we're incredibly special, or that something deeper is at work? Or is fine-tuning an illusion arising from our limited understanding? As we search for a theory of everything that would unify quantum mechanics and gravity, perhaps we'll find that many apparently independent constants are actually related, reducing the number of free parameters and diminishing the fine-tuning problem. Or perhaps we'll discover evidence for a multiverse, transforming our conception of reality. For now, the values of constants that permit our existence remain one of nature's deepest mysteries. The universe may be a computer simulation, and we cannot know for certain. One of the strangest possibilities that serious scientists and philosophers have considered is that the entire universe might be a computer simulation. a kind of elaborate video game or virtual reality running on some enormously powerful computer. This simulation hypothesis suggests that we, along with everything we observe, might not be physically real, but rather information patterns in a simulation. The idea sounds like science fiction, but it raises genuine philosophical questions about the nature of reality and has been discussed in peer-reviewed academic literature. The simulation argument was formalized by philosopher Nick Bostrom in 2003. Bostrom's argument goes as follows. Suppose that civilizations eventually develop the ability to run detailed computer simulations of conscious beings. If this is possible, then advanced civilizations might run many such simulations, perhaps to study history, explore alternative scenarios, or simply for entertainment. If many such simulations are running, there would be far more simulated consciousnesses than real ones. A civilization might run millions or billions of simulated universes, each containing billions of simulated conscious beings. Therefore, any given conscious mind, including yours, is statistically more likely to be in a simulation than in base reality. Bostrom doesn't claim we definitely are in a simulation, but he argues that at least one of three propositions must be true. Either civilizations almost never reach the technological maturity to run such simulations, or advanced civilizations choose not to run such simulations despite being able to, or we are almost certainly living in a simulation. If the first two propositions are false, meaning civilizations often develop the capability and choose to run many simulations, then the third must be true. Some physicists have suggested that certain features of the universe are consistent with the simulation hypothesis. The universe appears to have a smallest scale, the Planck length, below which current physics breaks down, somewhat analogous to pixels in a computer display. Quantum mechanics includes apparent randomness that could be interpreted as computational shortcuts. The speed of light limit might represent a processing speed constraint. The universe follows mathematical laws that could be viewed as the program code of the simulation. However, these observations have conventional explanations within standard physics and don't require simulation. The simulation hypothesis is difficult or impossible to test empirically. If we're in a simulation sophisticated enough that we cannot tell, then by definition we have no way to detect it. Any apparent glitch or anomaly we might discover could be explained either as a simulation error or as new physics within a real universe. Some researchers have proposed looking for computational limits or artifacts that might indicate simulation, like finding that the universe performs computations more slowly under complex conditions, as if the simulator's processor were being taxed. But no conclusive evidence of this nature has been found. The hypothesis raises profound philosophical questions. If we're in a simulation, does that make our existence less real or meaningful? The pain and joy we experience, the relationships we build, the discoveries we make would still be real to us, even if implemented as software rather than as fundamental physics. Perhaps the substrate doesn't matter, only the patterns and experiences. Moreover, the simulation hypothesis doesn't actually explain existence. It just moves the question back one level. The beings running the simulation would still need to exist in some base reality. That base reality would still contain a universe with physical laws and, presumably, would face its own questions about fine-tuning, origins, and the nature of reality. Simulating the entire observable universe with its roughly 10 to the 80 atoms would require computational resources that seem physically impossible. But simulating just the part of the universe any given observer can perceive might be feasible. The simulation might only render in detail what's being observed, like a video game that only fully processes the part of the world the player can see. This would be consistent with quantum mechanics, where systems exist in superposition until observed, after which they collapse into definite states. Some philosophers argue the simulation hypothesis is unfalsifiable and therefore unscientific, neither provable nor disprovable. Others suggest it's metaphysically interesting but practically irrelevant, since even if true, we still must live our lives and do science as if the world is real. The simulation hypothesis has entered popular culture and generated extensive discussion, but it remains speculative philosophy rather than established science. It serves as a thought experiment, highlighting how little we truly understand about the nature of consciousness, reality, and existence. Whether our universe is a physical system or a simulated one, the same mysteries remain. Why does anything exist at all? Why these physical laws rather than others? How does consciousness arise? What is the ultimate fate of the cosmos? And in pondering these questions, whether our thoughts arise from neurons in biological brains or from bits in some unimaginable computer, we engage in the ancient human quest to understand our place in the grand scheme of existence. The ultimate fate of the universe remains uncertain. We have explored cosmic mysteries from the largest structures to the finest details, from the moment of creation to the far future. Now, as our journey approaches its end, let us consider the ultimate question: how will the universe itself end? The answer depends on factors we do not yet fully understand, particularly the nature of dark energy. If dark energy is truly a cosmological constant, unchanging as the universe expands, then the cosmos faces a long, slow fade into darkness called the Big Freeze or heat death. The universe will expand forever, with the expansion gradually accelerating. Distant galaxies will recede beyond the cosmic horizon, their light unable to reach us no matter how long we wait. Eventually, only the local group of gravitationally bound galaxies will remain visible from our vantage point. All other galaxies will have disappeared, racing away faster than light can travel. Stars will continue to shine for trillions of years, but gradually the universe will exhaust its fuel for star formation. The last stars will die perhaps 10 to the 14 years from now, 100 trillion years in the future. These will be small red dwarfs, stars that burn hydrogen so slowly they can shine for tens of trillions of years. As the last stars flicker out, the universe will grow dark. Only remnants will remain. White dwarfs, the cooling corpses of sun-like stars. Neutron stars, the collapsed cores of massive stars. Black holes, which will persist longest of all. For an incomprehensibly long time, these objects will slowly cool, radiating away their remaining heat into space until they approach the temperature of the cosmic background radiation, which will itself have cooled to nearly absolute zero. But even black holes do not last forever. Through Hawking radiation, they slowly evaporate. A black hole with the mass of the Sun will take about 10 to the 67 years to completely evaporate, far longer than the current age of the universe. The supermassive black holes at the centers of galaxies, containing millions or billions of solar masses, will persist until approximately 10 to the 100 years from now. After the black holes evaporate, the universe will contain only a thin gas of photons, neutrinos, electrons, and positrons, growing ever more dilute as space expands. The temperature will asymptotically approach absolute zero. Entropy will approach its maximum. The universe will reach a state where nothing can ever happen again. A state of perfect equilibrium and ultimate stillness. This fate, while not violent, is in its own way final and absolute. Alternatively, if dark energy strengthens over time, the universe faces the Big Rip. In this scenario, the accelerating expansion becomes increasingly violent, eventually tearing apart galaxies, stars, planets, and finally atoms themselves as described earlier. Current observations suggest the Big Rip is unlikely, but cannot be entirely ruled out. If it occurs, it would happen perhaps 100 billion years in the future, though the exact timing depends on how rapidly dark energy strengthens. A third possibility is that dark energy weakens or reverses, causing the universe's expansion to slow and eventually reverse. This would lead to a big crunch, where all matter and energy collapse back together, perhaps reaching infinite density in a reverse of the Big Bang. Some cyclic models propose that the universe might oscillate, with each big crunch followed by a new Big Bang, creating an eternal cycle of expansion and contraction. However, the second law of thermodynamics, which states that entropy always increases, poses problems for simple cyclic models. Each cycle would have higher entropy than the last, and it's unclear how a new Big Bang could emerge from a high-entropy Big Crunch. More exotic possibilities exist. Perhaps the vacuum of space is metastable, and a quantum fluctuation could trigger decay to a lower energy vacuum state. Such vacuum decay would create a bubble expanding at the speed of light, fundamentally altering the laws of physics within the bubble and destroying all existing structures. This could happen tomorrow or never. We cannot predict. Perhaps the universe will experience a phase transition as it cools, similar to how water freezes into ice, fundamentally changing its properties in ways we cannot currently predict. Perhaps quantum effects or phenomena we haven't yet discovered will become important at extremely long timescales, leading to outcomes we cannot foresee. The ultimate fate of any observers or civilizations in the far future is even more speculative. Could intelligence and consciousness survive the heat death of the universe? Some physicists have proposed that sufficiently advanced civilizations might find ways to exploit the remaining energy even in a cooling universe, perhaps existing as patterns of information processing that become increasingly slow and diffuse but never quite cease. Others suggest that consciousness might be fundamentally limited by the availability of free energy and must eventually end. These questions blend physics with philosophy. What does it mean to exist in a universe approaching heat death? Can consciousness or meaning persist in such conditions? Or is life ultimately temporary, a brief flowering in the long history of a universe that began in a hot, dense state and will end in cold, diffuse darkness? For now, these questions remain unanswered. The ultimate fate of the cosmos depends on physics we do not fully understand, particularly the nature of dark energy and the possibility of physics beyond our current theories. What we do know is that the universe will continue evolving for timescales that dwarf the current age of the cosmos. We live in what is effectively the very early universe. 13.8 billion years is nothing compared to the trillions or googles of years ahead. In this vast temporal landscape, in this incomprehensible expanse of future time, we exist as brief observers, consciousness and curiosity arising in a universe that began without either and may end the same way. And now, with the final mystery softly contemplated, let the wonder settle gently around you. We have drifted through 100 mysteries of the universe, from the invisible matter holding galaxies together to the question of whether we are alone, from black holes where time stops to the uncertain fate awaiting all things. Through this long journey, a pattern emerges. The more we learn, the more we discover how much remains unknown. Every answer reveals new questions. Every solved mystery hints at deeper mysteries beyond. This is not a failure of science, but its greatest triumph: the recognition that the cosmos is vaster and stranger and more wonderful than we ever imagined. You are part of this mystery. The atoms in your body were forged in stars that died billions of years ago. The water in your cells has cycled through Earth's oceans and clouds for millions of years. The oxygen in your breath was produced by ancient microbes and modern plants. You are not separate from the universe, but a way the universe has become aware of itself. Matter arranged in a pattern complex enough to contemplate its own existence and wonder at its origin. Somewhere in the dark between galaxies, new stars are being born. Somewhere in the depths of an alien ocean, perhaps beneath the ice of a distant moon, chemistry might be stirring toward life. Somewhere in the future, observers we cannot imagine might look back at our era and wonder what we knew and what mysteries we pondered. The universe continues its long unfolding, expanding, evolving, perhaps creating conditions for new thoughts and new wonders we cannot foresee. So, wherever you are, allow your mind to rest now in the vastness we have explored. Let your breath slow and your thoughts grow quiet. Let the mysteries we have encountered tonight remain with you not as problems to solve, but as invitations to wonder, as reminders of how little we know and how much remains to discover. The journey through cosmic mysteries never truly ends. It simply pauses here, in this moment, in this breath, under whatever sky you call home. Sleep well, and may your dreams be filled with stars and questions, with distant worlds and impossible possibilities. Thank you for wandering with us through the universe's deepest mysteries. Until we meet again among the stars, rest peacefully and keep wondering.